You're audible and visible also.
Sorry, I'm visible now.
No, the video is off now. Video is off now. Now the video is on. Yeah, we can see it now.
Okay. Should we start?
Yeah, you can start now because the streaming is on. Recording can start.
Am I audible?
Yeah. Hello. You're audible, but the camera is positioned.
Okay. Yes, yeah. It is fine, sir. We can start, fine. Sir.
So we can start now.
Okay. So, good morning to all. Today, we have the eminent speaker, Dr. Kuntal De, with us. I welcome Dr. De. Dr. De is an eminent researcher and he is a very bright scholar. He has completed his BE from Jadavpur University in 2001. Then he has completed his MTech from IIT Mumbai. After that, he has completed his PhD from IIT Delhi. And during that, he had, after the service period, he had started his career in the TCS lab, IIT Bombay. After that, he joined in the Veritas Software, then Microsoft India Design Center. After that, he joined in the IBM Research Lab, and currently he is working as a technology R&D senior principal in the Accenture Technology Lab, Bangalore. He has more than 65 research publications. He has received 85 patents and filed 180 patents. His technical experience is more than 18 years, and he has received lots of awards. Among he has received the achieved twice the IBM Research India outstanding for his outstanding technical achievement. IBM Master Innovation that got twice, and member of IBM Academy of Technology, and participating member of SC42, the Indian government internal and international board of standardizations of artificial intelligence. We have in syllabus committee and advisory for the several universities such as IIT Guwahati, IIT Gwalior, etc. This is the program committee members and frequently review the most of the world leading AI conference such as AAAI, IJ, SCI, SCL, EF, NLP, Colin, Eric, and the other member of advisory committee of Center of Linguistic Science and Technology at IIT Guwahati, and other associately co-guiding 3 PhD students at a various stage of their PhD in IIT Guwahati. I am requesting his Dr. Kuntal De to deliver his speech.
Thanks, Dr. Farikar. It's very nice to meet you and to be here. Thanks for inviting me. And good morning, everybody. Good morning, Dr. Farikar, and good morning, everybody. And thanks a lot for your introduction. I hope I am properly audible and visible.
Yeah.
Is there any break of voice? There's a slight break of voice when I was listening, so I was not sure that it was my end or not. So is my voice consistent, clear, and streaming?
Now this is for my end. My network is creating problem. That's why I've been able to join late. You are audible here.
I see. That's great. Yeah. Now, okay, I typically use Zoom at work, so I'm not too sure how to share my screen. If somebody could help me on that, then that'd be really good.
Yeah, Prem.
How do I share my
So,
screen on Zoom?
sir, in your Zoom interface, you
Hmm.
can hover the mouse at the bottom. There is mute, start video, and after
Oh
that
yeah, I
there is
see it. Okay, okay.
participants.
I see the option. Yeah,
Yes,
yeah,
sir.
I see the option. I see the option.
Yes, sir.
Okay, so let me share the screen. Excellent. I can share the whole screen. That should be fine. Is my screen visible?
Yes, sir.
Yes.
Fantastic. So let me get started. So good morning to everybody who is attending here, and I hope we have a fantastic session today here now. And if I speak too fast, I have a habit of talking too fast. Just make me stop, because I know it's not very easy to make over the internet. The connections might not be too stable all the time, right? So the topic that I'll cover today is cognitive natural language processing using eye gaze tracking. Now, in a very short sentence, what that means is look at the eye gaze, the eye movement of people who are reading text, and try to add the semantics that we can derive out of that movement into the process of, let's just call it, doing natural for the time, go in more detail as we progress with the discussion, right? So before I proceed further, a lot of material is one of my, like, let's call it an informal PhD student, because I was not the formal guide. So that was Professor Pushpa Bhattacharya. But no, I mean, I was also like almost co-guiding him, at least for the half of his PhDs. That was Dr. Avijit Mishra, who was doing in IIT Bombay. So this work was done jointly in IIT Bombay and IBM Research India, out of the Delhi and Bangalore, right? So I think that's what the work is from, and this is not being pursued any further. I mean, I'm like pursuing very mildly, because that's not my main project anymore, and I'm not in IBM anymore. But yeah, I mean, there's a lot of research potential in this, so I thought it's a good topic to present, because this is a very interesting topic, and hopefully it might help everybody else also to think along these lines. At least whoever is interested to think along these lines, and can be derived, or how things can be better in the space, right? So that's it. That this is more from a researcher to co-researchers. And okay, I'm getting a message here. My internet connection is unstable. The moment you hear something break, just let me know. I can at least switch off my video so that I can do the best that I can in spite of the constraints, right? Okay, so that said, let me show a video first, and I hope I'm fully visible here. Let me show a couple of videos. So please look at this one. Okay, this, I'll tell you what it is, but for the timing, just enjoy this. It's a little longish, so I'll stop. I won't take the full time, but just look for the first few minutes. Okay, so let me take a pause here. I hope you people could see the video, and if not, just speak out, please, because I cannot see my screen right now, and I might not be following the chat window all the time. So I'd more prefer a verbal interaction if possible. That said, any guess, anybody from the audience, any guess on what you are seeing so far?
Participants can put the answers in the question answer section or in the chat box.
No, please.
Participants can, yes, sir.
Mhm.
So,
It just, sir, can I say?
Yeah, of
Sir,
course.
yes, it was just reading the eye gaze on the words in the sentence.
Yeah, perfect. That's exactly what it was. So some students, so let me just wind back a little bit, and maybe let me just let me replay this thing while I speak. So if somebody wants to watch, they can watch. So this is actually, I'm so sorry. So this is actually a piece of text from the science book of class 7. And we have made a class 6 student, not one, there are multiple, but this is just a sample of one student. So we have made some class 6 student sit in front of the text and make him or her read this, right? I don't know, it's a him or her, they are both genders, but make him or her like, read this thing and then look at how that eye follows, right? So there's an additional generator of pixels. Yeah. So that's exactly how the person read the thing. Now, if you look at it, what are pretty interesting in this, right? It's not a linear read. So what are the things that strike in our minds? Again, if the audience could speak out, that'll be fantastic. If not, I'll carry on. Okay. So let me say, somebody wanted to answer? Sorry.
No, sir. So there is no questions.
Sure. No, not a question. I was just trying to figure out if someone wants to, like, answer this. But okay, if I look at, okay, let me repeat it, or maybe no, I can just keep going. I can keep going. If you look at, so because there's more, right? If you look at the thing, this is not a linear read. It's not like the eye is going just straight forward from the first word to the last word at the same linear pace, etc. There are many things that we are seeing. We are seeing back and forth within the sentence. We are seeing back and forth across the sentence. We are seeing people pause at certain words of a sentence. And we are seeing people, like, really skim through, right? Not exactly read in some words, right? Plus, we are seeing, if you look at the point, right, they're like following and friction, right? Force and friction. Like, they're just jumping between words. The eye gaze is mostly jumping between words. By the way, this was done on a 500 frames per second kind of camera, right? Which is quite fast. It's like 1 frame per 2 milliseconds, which is typically like fast enough, right? I mean, for the timing, trust me, that's fast enough. Why is 2 milliseconds fast enough? There's literature to show that anything like up to 30-40 milliseconds is fine, right? So I'll go into those terms and definitions in a few moments, right? So if you look at it, right, so when they read the text, they are trying to understand by going back and forth. Then they answered a recall kind of question. Now they're trying to answer an understanding kind of question. So there are different kinds of questions that are very prevalent, right? Then there'll be application kind of questions, right? So they're trying to understand the question, they're trying to go to the answer, they're trying to relate. Now, at this point of time, I suppose there's not much more to show in the video. It's probably obvious by now. So let me stop this video. Now, not sure the presentation. Oh, I didn't start the presentation. I didn't go ahead, right? Okay, so that was pretty interesting. Now, before I even go a step ahead, let me just very quickly. I might be using these terms interchangeably. So let me very quickly tell what these are. So first of all, when somebody pauses at a word, like the eye gaze pauses at a word and stays there for, let's say, couple of hundred milliseconds, that's what we call a fixation. Okay, so I shall be using these terms pretty freely. But what's a fixation? It's the amount of stay that a word has, that the eye has made on a particular word. Then there's a concept of saccade. S-A-C-C-A-D-E. S-A-C-C-A-D-E. Saccade. Saccade is when the eye moves from one point to another, point A to point B. Now, for the purpose of NLP, if we translate those points as in pixel points into words, the words that are appearing at that point, that position, we can think of that as the eye moving from one word to another word. So there are two kinds of saccades. One is a forward movement. That is when the eye moves from one word, let's say word number K, to word number K plus delta, where delta is a positive number. So it's a forward movement of the eye, right? You are at the Kth word, now you're at the K plus delta word. I mean, take delta as an integer, right? Pretty much positive integer. Now that is one. Now that's where you call the forward saccade. The eye is moving forward. The other one is a regressive saccade or a backward saccade. That's when the eye moves backward, and we saw a lot of that in that example, right? So the eye was going somewhere, then there's probably a stumble point, and then the reader would come back a lot towards the back. One quick question, Dr. Farikar. I can go on for 2 hours and even longer, but do we plan to have a small question answer session, let's say after 1 hour and 45 minutes, or should we keep it like throughout interactive? What's a good way? Do you have any particular path that you follow?
Yeah. You get over at 45 minutes. 15-minute question answer.
I'm sorry, your voice broke. Could you please repeat? I'm very sorry.
You can get 10 to 15 minutes for question answering, and you can continue
Okay,
as
15,
per
20 minutes
your
for
plan.
question answer. Sure. Yeah, I think that will be a good idea because otherwise people might think of asking something later and never have an opportunity, right? So okay. So whenever you want to ask a question on the fly, please do that. Otherwise, at the end of like 1 hour, 40 minutes, 45 minutes, we'll have a short 15, 20-minute question answer session, right? Let's call it a 15-minute session. I think let's do it that way. Fantastic. Okay. Now, okay. So before I go into the NLP part of it, let me just digress for a moment. Obviously, the main talk will be on how to do all these techniques, and I'll talk of some papers we had, ACL, AAAI, CoNL, etc. Right. So I'll go through all of these details, and the both graph-based approaches that we had and deep learning approaches that we had, on top of, right, obviously usual NLP techniques. I'll go into all of those. I'll go into all the techniques and technologies, sciences, right? Before going that, let me just take a moment of digression and share this thing that, okay, eye gaze tracking is interesting not just for NLP, right? So while in IBM we were building a system on mobile, so this one obviously was a dedicated hardware, right? So these are different hardware. So there are different hardwares available. They're available from a company called Tobii, TOBI. Then there's something called iLink, right? Then there's something. So this one was an iLink thing. Then there's things called iTribe, and there are all kinds of costs. Like I've had one eye tracker for $99, which is obviously not much. I mean, it's just a few thousand rupees, less than 10,000 rupees. This one that you saw now, I forgot the cost. It was before my, I mean, when it was IIT Bombay had purchased it independently before we, and from IBM I was doing this independently before we paired up. But I think this one cost them like 20-30 lakhs. It was very expensive at that time. So yeah, I mean, the cost can be at any range depending upon what you want. Tobii in particular has a lot of hardware available. So I mean, they have different specifications, different functionalities, different tech specs, and then obviously different prices for those. Right. So I mean, if somebody wants to start this area up, you've got a cheaper option, you've got a more costly option, and then obviously stuff that I was trying to do while in IBM, it was a software-based system. It doesn't have to be a hardware. You have got your mobile front camera, you have got your desktop camera, the very one that you are seeing me via now, as a laptop, whatever. So you could always use those cameras and try to do geometrical projections or other ways of deep learning to project that onto the screen. Like, look at the head pose, look at the eye center, try to make a good guess of where this reader is looking at, and then do the processing based upon that. So very obviously, it's not a dedicated hardware. There'll be a lot of head movement unless you fix it in somewhere, right? And there are very practical challenges, right? The device can move, the human can move. If it's a laptop, then the angles can change, right? And you might be in a vehicle, so there might be a lot of jerking. So there's a lot of challenges. It's a very exciting but very challenging area to even capture the eye gaze properly and be able to pack that back into the right set of words. And then obviously that once you have the images, there's a question of processing, right? Because mobile phones are limited processing, obviously it's going up with time. Then nowadays the cameras are better, but there's a question of how good the camera quality is, right? So this one was many megapixel. The video you saw, I've forgotten how many, but quite a few megapixels. Nowadays the mobile cameras were better, but I haven't tried with 2 megapixel cameras with, let's say, 30 milliseconds, like 30 frames, 1 frame per 30 milliseconds, like 30-35 frames per second kind of. While this one was 500 frames per second, right? So you might miss information, right? And you might have wrong information. So there might even be a question of approximation based upon a few, rather than looking at one, especially when you're using a low-end device, rather than looking at one point and deciding, oh, this is where the participant is looking at. If you really have a low-end device, you might even want to make a time series, right? Maybe a neighborhood, temporal, local neighborhood, and then try to predict what's the most likely path that the user followed. Given two factors, A, the gaze itself might not be linear, but B, there might be a hardware issue also. Again, validating those things are very hard because the user might not even remember, so human annotations might be very hard. But again, those are nice open problems that you can look at. Now, that said, while IBM system obviously would be the proprietary one, but if anybody wants to play around, there used to be a lot of universities, but I think the one that has been really good of late is the OpenFace stack by CMU, the Carnegie Mellon University's, led by Louis Philippe Forency, right? So he was in EPFL earlier. He has moved to CMU. His stuff, I mean, the OpenFace thing is pretty good. Otherwise, Cambridge had their stuff and EPFL had their stuff, and I suppose Max Planck also had some stuff around it. So there are university things that you can probably download and play with also. OpenFace definitely is the one if you really want to try. OpenFace is definitely the one. I have not tracked it over maybe the last year, couple of years maybe, because that's when I moved out of this space and then obviously moved into Accenture. That was earlier this year, but I mean, I was just moving out of that research area because of IBM's focus also. Right. So yeah, anyway, so that's for it, right? If anybody wants to play with that, then OpenFace is a good software. I'm not sure it's free or not. It probably should be. It used to be. Yeah, I mean, non-commercial thing probably was free from what I recall, but obviously the licensing terms might have changed, so you might want to check it out. So yeah, I think that's what it is. Now applications is far from just NLP, right? Let me just show a couple of other videos that I have. Maybe that might be quite interesting. Let me show this one maybe. So I know this is a bit of repeat for the first few seconds. Maybe I can shortcut this a little. Hold. Yeah. So this is something I've seen if it's a collage of videos. Look at this one. This asks the system to find Obama, and just give me a moment. I want to replay this again. Yeah. If you heard this interaction, I'm sorry. If you heard this interaction, the system says find Obama. Okay. Now, if you look at the laptop carefully, you see just below the laptop, where the screen touches the keyboard, you see a device there, a black-looking thing with a silver edge. That's actually an iDrive device. The thing that's saying was $99. It was, I think it was made in Denmark or Norway. I think it was Denmark. Quite some. This I got in 2015, so it was quite some time back. So this was one of my students. He was trying to do a contactless interface and that's very applicable by the way. In today's COVID kind of situation, having such an interface is very appealing because you can look at things and not touch things, right? And then be able to still survive. Okay, so that's something doable. So what you have here is this person was looking at this and that, and they had a contactless interface. They're gazing at things through the eye. And if in this implementation, if they looked at something long enough, that would be clicked. But obviously, you can have a different gesture, right? If somebody looks at something and let's say blinks or presses one eye hard or whatever, they can click, or maybe point or something, it can be clicked. The whole point is this: it's a contactless interface, right? So if people, if any of you the faculties or the PhD folks or anybody, if anybody is doing this sort of like contactless interface research and particularly applicable for COVID situations, here's a very nice thread you can follow up if you are really willing to, right? And yeah, I mean, if anybody wants, obviously, I would be happy to look at this also if somebody really wants. But I mean, these are very nice opportunities that are coming up, right, in the near future. Okay, so this is one of the things. I mean, I'm already thinking around that, but let's see. So this is more of contactless interface. Let's say it's an app. See, they clicked on home, they clicked on fruits, find apples. So find piano, right? You see the instruction on the screen, find piano. Okay, so we'll move on to the next part of the video now. So far what you have been seeing, in both the videos, right, the eye gaze tracking one as well as the contactless interface one, that was tuned for an individual person. It was just tracking one person and clicking. Now, if you look at this one, here we have a group of people, right? So think of a classroom kind of situation. If you really want to look at how which parts of the text, let's say the whiteboard text that the students are following, can you do a classroom mass tracking of the eye? Like, can you make out what the generality is looking more at? Can you create a profile of your, let's say you're presenting a text material in your class. Can you figure out what are the parts of the text they're looking at more? Or can you figure out where are they struggling, right? Let's say they're going a lot of back and forth, right? So they're probably trying to either a hard concept or they're struggling, right? So what might seem easy to somebody as a teacher might not seem equally easy to some of the students, all of the students, whatever, right? So this can give a sense of that. And obviously, I'm just talking of the classroom situations here, but there are a lot of other applications also. If you look at, like, for example, if you look at, let's say, I don't know, maybe a trade show, for example, where people are demoing a lot of products. If you try to look at the audience and see where majority is looking, here's a way to do that, right? You're displaying 5 items together, but what's the item that's getting a lot of eyeballs? That's a retail or this sort of a thing, right? So there are many other situations possible. Let's not go into all of that, but I'm sure you can think of many also. And we actually had a lot of use cases. Like for okay, I'll take another one, right? So if you are looking at the, let's say, that if you look at any sports event, the teams. So there are two angles: A, the team, and B, the referee / umpire. All of them need to be looking at the right set of things, right? So can you look at the team members' attentions and better coach the team where to focus in what kind of situations at what time? That was one of the use cases we had. Then if you look at umpiring, refereeing, then you can really track all the referees in a football kind of soccer kind of thing. It's a linesman, right? You can, or maybe for a tennis, there are ball people. You can really look at their eye gazes and A, you can evaluate them. B, you can question their calls and so on and so forth, right? Like in a football soccer game, right? Are these referees really paying attention to the ball? Are there really penalties happening in the right way, etc.? So there are a lot of use cases you can do through this sort of a thing, right? Anyway, and if you notice this, these users are not even wearing a headset or something. It's just a fixed camera. Now that said, let me proceed on with the demo. And if I'm speaking too fast or if I'm speaking too dense, just raise your hand and let me know. Just speak out and let me know. Thank you.
It is okay, sir.
By the way, this one was done from an iPhone. If you saw the fifth person who came from the backend, it was actually done by an iPhone, and this is the IBM Research Labs library, part of the library, actually, a corner of the library. So he just placed the phone somewhere near a board and came here. And so that was some of the use cases. I'll actually show a couple more and then go deep into the NLP side of things. I'm not sure what this is. And this is the final one I'll show and then go into the NLP, because I know the main focus is NLP, but you can actually have a real. This is a very very monotonic thing. So I'll just stop in a few moments. So if you look at it, it says that so this is an e-commerce store for books, and obviously we are just showing here. You are gazing at this book, that book. Again, this was recorded. Okay, we didn't show the person. Somebody was looking somewhere, and this thing was a mobile app screen in the vertical or whatever you call it, right? Landscape. I'm always confused as landscape or portrait, but you can make out what I mean, right? It's on the long side on the horizontal, right? So essentially that's what it is, right? This will continue for the next 2 minutes. There's no point in watching all of this, but you can always figure out what books you are looking at. Obviously, here we are saying you are gazing at this, but you can add an automated, add to cart kind of button. You can even create a secondary cart that you looked at these things, but you never looked at it. You can use that for upsell, downsell in commerce, right? If somebody is really interested going back and forth, you might actually offer a better deal, better price, whatever, right? So there are a lot of things you can do with this. This is a mobile app for e-commerce, right? And again, there are other stuff that we have. Like for example, there's a patented material we have. I think it's granted, but whatever. Let me talk of that also, and that's the final thing I'll talk of before I go into the text material here. So that one is, in fact, if you look at Google AdWords, what does it do? It auctions the space on google.com, right? It auctions the space on google.com, and what it does on top of that is, if you are paying them more, they'll place your ad at a better and more visible position. If your ad is relevant, or and they have a thing called ad quality score. If your ad is more relevant, if you've got a good product that's getting, or whatever, good ad, I don't know what, but getting a lot of click-throughs, then they'll obviously make you pay lesser to get the same result, which is effectively they are making better products to come up at the top, and that's based upon audience reaction, etc. So that's purely in the digital space. Now I'll hereby draw a patented stuff that we have, which is absolutely the physical space, but a corresponding thing of that. And it's not, by now a light bulb might have clicked in your minds, but still, let me describe it. What we did there is, think of a retail store. I mean, I'm pretty sure all of you go to all these physical stores, like, I don't know, maybe Big Bazaar, Pantaloons. There are a lot of brands that we all go to, right? And Central, whatever. So when we go there, if you think of installing small cameras, right, probably costing 500, 1,000 rupees, at each of the racks, then what happens is for each person or for the mass, if you don't want to like identify people, if you want to keep things private, but then at least the end mass, you can figure out what are the products that people are looking at and for how long. Now, if you try to overlay that with the physical location of the rack on the store in the store where the product rack is, right, where the products are placed physically, where like the location, which aisle, height, and so on and so forth, right? and so if you do a product profiling based upon that, you'll eventually get a sense of whether people are really looking at the product or the location, and that will give you a sense of which products are good and which locations are good. And then eventually you can use this information to either auction some of the positions. If it's about the store, let's say some locations are very good irrespective of the product, then you can actually auction those locations to retail companies, retail brands that want to place their products there. Or you can keep your more profitable products in those locations, right? Or you can actually negotiate better wholesale deals based upon those profiles, right? You can also look, company X, if I put your products in this location, then you are going to make more sales. Now, would you be willing to give, like, I don't know, either more products or a better credit rating or a better discount, whatever, based upon that, right? So, as I said, the whole space of eye gaze tracking is massive, as you can very sense, and I'm pretty sure some of you have thought of it before. But for those who have not, right, it's a very, very interesting space indeed. Okay, now that said, let me not digress any further. Let me totally focus on the cognitive NLP process using the eye gaze tracking, this main topic of the talk. So, so what's the underlying idea? The NLP tasks, there will be a lot of NLP tasks. It can be sentiment analysis, sarcasm detection, others can be anything, right? I mean, I wrote these two because these are the two areas that I'll be presenting here. Now, there will be raw text, then there will be annotation. Let's say the annotation can be, okay, this sentence has positive sentiment, that sentence is sarcastic, whatever, and there are many other things, right? You can look at sentence pairs and find paraphrases, irony, pun, whatever. I mean, look at individual sentences, find out irony, pun. You can do part of speech tagging, name entity tagging, lot of things you can do. But I'll just take this two as example. So there's raw text, there's annotation, which gives you label data. And you can actually have, so apart from the usual annotation, what we are also adding is to have cognitive data to EEG, MEG, eye tracking, key logging, etc., etc. So we'll be adding the eye tracking part. We will not be doing EEG, MEG, etc. Right? And then using that, you can gain insights to the cognitive aspects of language processing or humans' language understanding method or capability, etc., etc. And then eventually you can translate those insights into better NLP or natural language understanding, NLU algorithms, data systems, and so on. So what's the standard trinity of cognitive NLP? They're the NLP tasks, translation, sentiment, parsing, cost. There are infinite of these, right? All of you know those. Then there are languages. This can be English, Bengali, German, blah blah blah. It can be algorithms, which can be statistical, supervised, semi-supervised, and neural networks. It can be unsupervised if you're doing text clustering, etc., etc. Okay. Yeah, I think this slide has been borrowed from Pushpa Bhattacharya's. He was a
Excuse me, sir.
collaborator in the work.
If you can make it in the slideshow view, it will be better.
Yeah, that should be better. I'm sorry, I thought of doing that, but I somehow missed it. So is this more visible?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Yeah, I'm sorry for that. I just more like to try to this thing. So sorry for that. Yeah. So these particular slides, couple of them were from Professor Pushpa Bhattacharya's course, CS 626 in IIT Bombay. But anyway, he was a part of this work, right? So I mean, that's where we have the slides from, and I have this thing to use. So anyway, so we have got the NLP tasks like post tagging, parsing, machine translation, sarcasm, etc. We've got the languages, we have got the algorithms. But if you look at this, we are adding the human cognition factor, right? So we are adding eye gaze tracking, fMRI, brain imaging, whatever. I mean, those can be added. We are just adding the eye gaze tracking. But then if you look at the other things, those are also stuff that people interested can follow up on. Obviously, there's a huge amount of potential, and particularly the devices are improving very fast. So you can always put the easy kind of things because there are a lot of obviously fMRI might not be too easy, those sort of things, but there are almost like not very hard to put EEG devices that you can have like relatively lesser number of points, right, scopes, and get stuff done. Right. So yeah, Now the question is this: why do cognitive NLP? And it's probably okay and obvious by now, but let me very quickly read through. Most of the modern NLP systems are data-driven and they rely on text input, right? And there's a saturation barrier. So I mean, purely doing text is not giving much better now, right? In spite of deep learning, there are improvements, yes. But again, the moment what we're showing one of the papers we had is the moment you had deep learning, obviously standard deep learning, but you use IGES on top of that, there is an improvement. And we'll come into that. That was an ACL paper in 2018, right? So need to explore and exploit additional modalities like speech, image, stylistic patterns. There's cognitive information like a stronger modality, for example, it connects a cognitive underpinning of language processing and understanding, as in how a human thinks. And then there's brain imaging, EEG, etc., etc. They cannot be used outside laboratory, and they're very expensive, right? Very expensive. So the beauty of eye tracking, as I said, is you can even use the mobile and laptop, and that's what we are trying, right? Yeah, and that's why not just those, right? Now eye movement, so this is a very old word, but what this is like the whole work is based on this fundamental that when a subject views a word or object, he or she also processes the word cognitively for approximately the same amount of time he or she fixates on it. So let me take a pause here. What it means is, you cannot look to, let's say you cannot look at London and Tokyo. Let's just take a popular this thing, right? We joke around, but if you're looking at London, you're talking to London. I mean, if you're looking at a certain word, you're probably processing that word, not other words. Now, and I'm sorry if there's some background noise you're hearing. My door is closed, but I have a baby son at home, and obviously he doesn't understand. He's too small. He's like playing and shouting around. So if you hear too much background noise, please let me know and see what I can do about it. Now, gaze patterns. Yeah, now gaze patterns are believed to indicate this conceptual difficulty, right? So if you look at the term fixates, that term fixate is very important. If I take a moment, what I said a few minutes, if you remember what I said is there's a term called fixation. How long you look at a particular word is your fixation at that word at that visit, right? So now, and yeah, there's linear and non-uniform speed gaze movement is observed over text having similar concepts. And often non-linear movement with non-uniform speed, right? So this is also very obviously it correlates with what was like written this fundamental the I-mind hypothesis. The point is this, and very simply speaking, if it's a linear simple text, you'll just read it once and you understand, you are done, you'll probably just proceed on. But if there's some complexity that needs you to like reread the text, let's say the text is complex for whatever reason, then obviously you see a lot of eye-gaze movement backward and forward, regressive and progressive occurs. Okay, so that's what happens here. Now if I think out of it, oh, by the way, so eventually if you think of it, if you take a time series of this, of all the words that you're looking at and treat each word distinctly, if you're revisiting the word, then what you have is a long path of where which words I actually followed. That's called a scan path. And if you like, ignore the time for the timestamps for the time being and just look at which all words and which all traversals happens, that's something what you're calling a saliency graph here, but obviously you can give your name. That's not a very standard term. We are just calling it saliency graph for ease of reference. Anyway, so to come back to this, so if you look at the scan path of a non-uniform text is going to be much more non-linear and like more complex than the scan path of a linear text. So if you simply just give a blind look, forget any research, just collect the scan path data, give it a look. If you see the thing going back and forth, if you see a lot of fixations, if you see a lot of regressive occurs, not just progressive ones, then it's probably not an easy text to understand, right? So at a very baseline level, I mean, you can just use this very simple hypothesis as a baseline of text difficulty measurement, right? If you don't want anything else. So devices I have covered, these terms I have covered. Applications I have probably covered more than what's in the slide. Right. So as far as the actual research work was concerned, we did quite a few things, right? So the first one, I'll cover some papers that we obviously had more than this, but I'll just cover some of the papers that we published, and we had more papers also than this, right? These are just some of the key papers. So the first one is scan path complexity, a generalized model for reading and annotation effort, and it appeared in 2017, right? So obviously it's a good conference, as we all know. And So if you look at scan path, so what's the scan path complexity? From what I said just before, it's probably obvious. You look at how the eye moved. You look at how much of non-linearity is there, how much you go back and forth and so on and so forth, right? And then eventually you find out, eventually we try to measure the complexity of that path. And if you note, while we didn't try to explicitly take factor for it because our device was taking care of it, but do note that if your device is taking a high frequency noting, unlike a low frequency 30 millisecond thing, it's a high frequency note of points. There's actually an additional concept beyond what I mentioned here. That's called a microsecond. So, so what's the difference between a microsecond and a full second? Microsecond is, okay, there's a behavior of the human eye that it suddenly moves, let's say fluctuates for a very small time between a couple of points. Now, typically the timing for that has been measured to be anything less than 100 milliseconds and usually in the range of 30 to 50 milliseconds. So, so that's not a real movement, so that's, I will typically come back and usually 30 milliseconds has been shown to be less than enough for the eye to grasp something. Sorry, just a random muscle movement. But those might get captured, like if you look at this one, it was like 2 milliseconds per frame, right? So obviously those things will be captured here. So that needs to be like factored for. While a regular second will be like more than 100 milliseconds, let's say 200, actually quite a lot more, typically 2 to 300 milliseconds, sometimes lesser, sometimes more, typically lesser, typically 100 to 200, maybe 200 I would say on an average. So that's what a regular second is. So that's one part of it, but there's yet another part. See, it's ultimately there's a hardware and software aspect also, right? If you really have your laptop or whatever screen fixed, if you really have your chin fixed, then there will be relatively much less. And obviously, if your hardware quality is good, then the hardware errors will be minimal. But the moment you downgrade to like a lesser hardware, or you allow free movements or at least semi-free movements of the head, then the hardware might think there's a movement of the eye, which might not be the case. The humans are very accustomed to move the head very fast if something moves. Now, how fast it does very fast and how does that get captured in the hardware is a gray area still, right? And it's not a very obvious thing to solve either, right? So, it's probably an open problem, but it's not an easy open problem beyond a level of accuracy. However, the impact of that is this: that there might be a couple of very sudden suckers or hardware issues that might need to be ignored in the process. So that needs to be taken into account while the rest of the work is done. Right, and that also needs to be, that also obviously, a microsecond, for example, cannot be modeled as a part of your complexity of a scan path because it's not really a second. You have to look at the real second, the forward and backward seconds. So what did we do in this work? We measured the complexity of annotation effort by modeling complexity of scan paths as opposed to the total reading time, right? So if you look at the existing work, they typically look at the total reading time. How long did you take and what did you fix it on and so on. While this work really does a lot more. I mean, our work really does a lot more. It looks at the stuff that you're looking towards, but not as a sum total of time. It looks at several different aspects and then does an analysis also in several different aspects, right? Because when I say some text is complex, why is it complex? Is it because it's lexically difficult? Is it because the text syntax is, let's say, not very simple? Let's say, a lot of clauses, phrases, compound, complex sentences, or what's the reason? What's the syntactic reason? Then there's a semantic reason, right? Even a simple sentence might be semantically complex. For example, take sarcastic sentences. Let me take this example, for example, right? I went to this movie is worth going into because the film, the cinema hall has fantastic air conditioners. Take a moment to digest that. Is the movie good? Probably not, right? Because if the movie was good, you say this movie is worth going into because something positive about the movie. Let's say somebody put out a fantastic acting, right? Or somebody, let's say direction was fantastic, the background music, something, or maybe the total movie, the story was great, whatever. What you're saying instead is something which is completely unrelated. You are saying because this movie has the movie hall, the movie theater, cinema hall, it's got a fantastic air conditioning. That's not a reason you go to a movie, right? That's far from it. So you're being sarcastic, right? That's the only, what you're saying in reality is that's the only reason you go to this movie, that you get to enjoy some good AC, air conditioning for some time because the movie is not worth it otherwise. But if somebody puts that into writing, I'm sure it it will for many people. Now again, remember, it has to be a mass effort. I mean, somebody might be very smart and get everything at the first read, but practically speaking, that's not the case with human being as a totality, right? So some people will be getting things fast and some will not, right? So there'll be enough people reading this back and forth. So the moment I say this, one more thing becomes obvious. You cannot just look at one person. I see a few points. Just give it a moment here. Yeah, I'll just come to these answers. Just a sec. Okay, I think I lost it. What are they saying there? I'll just come to these questions. Yeah. So what I'm saying is this. Sorry, I was not looking at the Q&A. Then it suddenly occurred to me, and so on. I mean, I suddenly saw this, and so on. So I'll just come to these answers. Give me a moment. Now, I was talking about the scan path complexity. I'm so sorry, I just lost it a little bit. I was talking about the scan path complexity. Then I was talking of the lexical, syntactic, semantic difficulty. Yeah. So yeah, there I was giving the example of the sarcasm, right? So that's a case of a semantic difficulty, right? So you'll have all of these things as I go down, but if you look at it, it's not a linear challenge, right? It's not a linear challenge that it's not just so this thing can be from a lot of reasons, and we have to figure out that what are the reasons that are well captured by I-guess tracking and what are the places that it can really help. Like if it's a lexically hard sentence, does it really help to have I-guess tracking? If it's a syntactically complex statement, does it help? If it's semantically complex, does it help? Right. So we shall do a regression and we'll figure out, and we shall correlate the evaluation by correlating with different measures of lexical syntactic complexities and the readability matrix. And what we shall eventually observe is scan path complexity. This is a peak to the end of this paper. Scan path complexity will correlate well with multiple measures of lexical and syntactic complexities and readability, and baselines based on purely fixation or slightly advanced baseline of purely Saccard, right? So you cannot just, if you look at our models, we'll give a better result than just saying, okay, I paused at 5 places for this long, or I just moved this many times and I skimmed this many words, I read this many words. So this is more complex than that. Okay, now I'll go to these questions asked and let me see what they are, and then I'll go to the next slide. The first question is it possible to use the I-guess technology in online exam system? Exams on the screen during the, yeah, to an extent it's possible. I mean, you have to figure out if you look at the multiple people thing. Okay, so let me answer this in a slightly elaborate manner because these are very good research questions. Now, okay, the thing goes like this. And by the way, if I cannot answer something live or even otherwise, please feel free to write to me. And I would say no, write to me my personal email. So no, I'm just answering live. So I'm just answering this one live. Is it possible? Yeah. Is it possible to use the I-guess tracking in online exam system for observing the students of the screen? Yes, it's possible. Obviously, in an exam system, it can also be done in classrooms. But yeah, what you can do is in an online system, you can have your you have to mandate the webcam or whatever the laptop's camera or mobile's camera, whatever that's on, and then you have to track the head pose and I-guess. So you should just look at the head pose and the eyeball, and you can obviously combine those two to eventually detect the I-guess, because that's what is done. Typically, two things are looked at: the head pose and the eye center. So you can look at this, and you can definitely do that. And by the way, I have a very interesting paper. Obviously, I have many papers and many patents in this area. Just to give a sense of what can be done online, I actually have a very interesting paper here where I work with some autistic children, and as you know, right, autistic children cannot follow and focus well. So what we are trying to do in that work is we are actually trying to. So we have got to this one of the schools in Delhi, which is typically for autistic children, right? And then we had helped, we had deployed our system and was trying to make them focus better by having certain ways and having them learn better. And we are also trying to see if you try to improve the focus, where do they look at? First of all, where do they focus on? Because they have autistic children have a tendency of not focusing on the main object. It's very well known in the literature. Next, if you can make them focus on the right thing, then how do you do that, right? For example, can you zoom out something? Can you change the color of something? Can you keep their eye, let's say, is supposed to be at coordinate x1, y1, but they're looking at coordinate x2, y2. Can you actually shift your screen to show the main thing at x2, y2? Can you actually then maybe gradually shift back to x1, y1 as the person keeps looking at x2, y2 now, the object at x2, y2? Maybe create red circles or something, yellow flashes, arrows, right? So we looked at a lot of these things. So yeah, you don't have to look at anything, but yes, for an online system, you have to you can actually look at where the thing is, where the person is looking at. And for a classroom, by the way, so that also makes me answer this. Even if you do in a physical exam, you can actually set up cameras and try to really see whether a student is looking at their exam paper or they are trying to move their heads around, and you can actually create alerts if they are trying to copy from some other system. Actually, no, I discussed with, I won't go in the details because that's more of a business thing. But let's call, there's an initial discussion that we had started whether we should approach the government or not for things like UPS exam, right? I mean, you can always do that. So it's a very nice system that you can have because people can like copy from others. They can, they might not always be honest, right? Even for those kind of, it's a, and there might have genuine reasons of not looking at the screen or not looking at the exam papers in a physical system, but you can make out who is looking, who is not. You can alert. It's like somebody is looking away from too long or looking at too many times. You can create alerts. So does that answer this question? To Dr. Sanjay Kumar Pal, does it answer this question? So does it answer the question? Okay, thank you. So I'm just typing this as done. Achha, the next question is there a software to perform gaze pattern analysis? Okay, there's software to figure out, like I said, open face, for example. I'll also type. So I've also typed this thing for everybody's consumption. So, but let me also talk of it verbally. But so try open face from CMU. Now that will have your gaze points. You can obviously create your custom gaze patterns. What that will give is a time T1. You're looking at point X1, Y1. You can figure it out, and then the time T2 you're looking at point X2, Y2. How you create a pattern out of that is obviously your choice because that might be customized for your own application needs. And again, if it does not answer, let me know. I'm assuming it answers, but does it answer, yeah or no? This is Dr. Prashanjit Kundu. Does it answer? Yeah, if you have more questions, please ask. Or if it didn't answer, then just let me know. I'll come back to it, right? So let me carry on, but I'll hope to see your result here, see your response. Okay, excellent. So, okay, so let me carry on. Now, what's the method? So given, X is X1, X2, Xn, a set of scan path attributes, you can model it in two ways, right? So we'll be calling it, so scan path complexity H and L. So one is a heuristic, and as you can see, we model it as a theta X plus C. And the other is a supervised, which is sigma of Wx plus C, right? Now, heuristic is okay. In supervision, you might have a supervision on, there might be human supervision for reading difficulty. Now, what are the attributes that we use? That's very interesting. The gaze attributes we use are total fixation duration. Now, what is that? So, if I take a, if I rewind for a moment, if I recap for a moment, what was fixation? You look at word wy for a time duration d1, let's say, for example, right? Now again you move on to some other words, then you come back to this again, this word wy, then look at it for time duration d2, and so on and so forth. So once you are done with reading the text, that word wy, let's say, has been fixed upon 5 times, d1, d2, d3, d4, d5. Those are the five durations, right? Like first one was, let's say, 100 milliseconds, second time was 300 milliseconds, third time was 2 milliseconds, 100 milliseconds, etc. So total fixation duration is simply a summation of those, right? You simply do d1 plus d2 plus d3 plus d4 plus d5 plus whatever, and that's what it is with respect to that word. So this is a word level property. Each word will have a total fixation duration. Then there's a total fast fixation duration. So I mean, you have, yeah. So this is this. So for each of the words, these are sentence level attribute though. For each of the words, you'll be looking at that word either once or never or multiple times. There's only these three options you think of it, right? Some words you might never even fix it on. You might just skim through those, right? So that will be under a few milliseconds. So those will be just taken as non-fixations, right? But the words that you significantly focus on, which will be really counted as fixation because it goes beyond the threshold of, let's say, 100 milliseconds or whatever is set in the system, right? So the faster we look at that, you just count that, and the remaining times you come back to that word, you ignore those. So that's a fast fixation duration for that word, and you can sum total that. And then total regression fixation duration, that is the total fixation minus FFD. Because anytime you do a second fixation on a word, it's because of a regression, right? Remember, you might still be forwarding, but some regression happened, and hence you could forward and again reach the same word. Right? Otherwise, you would not be reaching the same word twice. Then there's a question of total fixation count. This is the question answer coming up. I hope that's the previous one answered. Perfect. Okay, perfect. Thank you. Then, okay, total fixation count is simply the count of all the fixations, right? And I'm sure that's obvious. Skip word percentage is the words that have never been fixated upon. How many or what percent of words did somebody never look upon? Then there's a question of total regression count. So that was okay. So if you look at this one, you have fixation attributes. Now the saccade fixation was when you look at a word. Next is the saccadic attributes, right? So when your eye moves from one word to another, either in the forward or in the backward direction, that becomes a basic saccadic attribute. So total regression count is the count of regressions. How many times do you go back and forth? Then, I mean, how many times do you go back, right? Not back and forth, I'm sorry. How many times do you go back? Then total saccade distance, and this is a forward saccade. How many times did you, how many characters did you move forward in terms of character count? I mean, you have to do in some sentence, right? Here we have done in terms of character count. How many characters do you go behind? And then total regression distance also similarly. How many? Sorry, saccade was forward saccade. Regression is like backward saccade. And then we introduced like complex saccadic attributes like a negative log likelihood, which is the negative of the log likelihood of saccade transitions with respect to an ideal saccade transition mode. So there's an ideal thing that you have, then and then the negative log evidently the next slide. So what is the saccade likelihood or unlikelihood, whatever you would want to call it? But so you have a model, right? So you have an expected this thing, right? You have an expected movement here. So the model is like the psi is the forward one and 1 minus psi is with the reverse. So what you do is, the asymmetric this thing of, okay, so there are two Gaussian curves. If you note, there are two Gaussian curves, and since usually you are likely to go forward, the forward one is bigger, and the forward one has a higher mu sigma, and the backward one has it lower, right? So is psi multiplied by this function that we are having, right? Mu of this thing, mu sigma of P1 and P2. So P is being the progressive saccade, and it need not be symmetric whether. So if you look at the curve, if you look at the forward thing, look at the right hand side wheel curve. So you see there's a mu P1 and sigma P1 and a sigma P2, right? So they need not be symmetric really. And then mu like the right, and you model this function as this way. So 1 by 1 upon z expression. I mean, you can read this thing, right? It's very hard to read out. I'll just pause for 30 seconds so you can read this up, and it's pretty straightforward. So I don't really suppose there is much of a question on this. But if there is, feel free to ask. I mean, obviously. If you really want, I can also refer to the paper, right? It's obviously available. So if you want, you can just figure it out. It's up online. I'll give a very quick pause now. Just look at this once, and I hope you know that becomes pretty clear. Okay, so I'll move on. Now, so the theory, like the model framework is now built, and here's the experiment setup. So we have to create eye movement database, right? So there's the student collections, the data collections that Avijit was the student, right? So he was a PhD student then, so he did that. And actually, he did a fantastic work. Also, he had joined, like, after he completed his IIT PhD, I had actually referred him to IBM Research, so he joined us, and he's not there anymore. He's in Apple USA now, but he did a fantastic job of this. And he was creation of eye movement database. There are 32 paragraphs from 16 different topics from the domains of history, geography, science, literature, and they are collected from Wikipedia. And by the way, there's a simple version of Wikipedia also, so that was collected from there. Documents were annotated by 15 participants. I'm sorry, participants, the S is missing, but in your mind. Then the task was reading followed by assigning difficulty scores, right? And the fitting, so we had this SCACOM, which I had showed before, right? So with the linear regression try to fit. And then there's an evaluation, right, which is rank correlation with textual attributes. So yeah, this is pretty straightforward actually. Now, once you know the thing, it's very straightforward. So what are the attributes that we looked at? There's a basic sentence, like the very basic NLP lexical properties, right? The word like word count, sentence count, characters per word, syllables per word, words per sentence, etc. Then there's some standard readability scores that are present in the literature, like FK, for example, is a very popular one, and then there are other ones also, right? The flesh insight is a very popular one. It's really one of the ones that has a huge number of citations, and it's very popularly used. But you see, there are three others that we used. Then there's a question of lexical complexity. So the total degree of polysemy, for example, and that's like, with wordnet senses of all the content words. Then the lexical, because obviously if you look at it, the moment the word has multiple senses, it does add to the lexical difficulty. Then the lexical sophistication, as proposed by Liu 2012, lexical density, which is the ratio of words to the number of content words to total words. Okay, what's a content word? Typically, it's verb, adverb, adjective, and noun, right? And the rest of it is like, your preposition, etc. Conjunction, preposition. They are not like articles. They are not content words. Then there's a question of outer vocabulary words, right? And then what's the ratio of that? And we have used like two very standard vocabularies. Then there are syntactic complexity measures like dependency distance, which is the distance of all dependent words in the sentence. Then non-terminal to terminal ratio. So that obviously tells you how many terminals and non-terminals are generated, and that will be a complex versus not kind of sentence in the syntactic sense. How many clauses are there per sentence? How many complex nominals are present per clause, and so on. So for this, obviously, there are standard, standard sources available. You can always use the standard, etc. Then there's a discourse property. So discourse connectors and coreferences, and particularly the distance of coreferences. And then eventually trigram kind of perplexities that the language models are trained on a mixed sentences, right, from the Brown corpus. And Brown corpus obviously is very popular, right? So it's a very standard thing that we can use without being questioned. How are the results? So on this slide, what I've showed is, okay, so if we go back, so there are 5 things, right? Lexical properties, readability score, 6 things: lexical, syntactic, discourse, and perplexity. First two are given here, basic and readability. So for basic properties, if you notice, the baseline does pretty good, right? For words and sentences, yes, it does matter, but the moment you go a little deeper, it's just a baseline that does better than any of the models, mostly, right? But the moment you go to readability, for most, like, obviously FK readability score does quite well. Our system does almost as well. Otherwise, for anything else, it's our stuff does better than that, right? So Spearman's rank correlation coefficients between various forms of scan path complexities and linguistic complexities, textual attributes, and readability measures, right? So, so I think, yeah, so that's what it is. It's those are those observations. Now, if I come to the other few things, right, lexical, syntactics, discourse, and this thing. Again, if you look at lexical, I'll go straight up. If you look at the basic properties, a lot of that is mostly lexical, right? If you look at words, sentence, clauses, so it's not really, maybe a bit of syntax, but I would mostly call it lexical. Again, if you come back here, the moment you go to the lexical complexity stuff is a baseline that does well, right? Our stuff, apart from just one of the things, our stuff doesn't stand, right? And for your reference, it's only for DP, which is a degree of polysemy when this thing stands, but lexical sophistication, density, outer vocabulary, the baseline is sufficient. But the moment there's syntactic complexity in the sentence or text, so that is when our stuff really starts beating the rest of the system. Maybe lexical baseline does well in one case, but everything else is our system. And if you look at discourse properties, like our system is like really a lot better than like in the baseline of 0.46. Perplexity is, again, it's like fixation L, but still it's a part of our system, right? It's not like, it's not like something random, not a baseline rather, sorry. And those are mostly statistically significant also. So I mean, that gives us confidence that it's a good thing. So I'm sorry, yeah. Now let me read out the observations to summarize. Scan path complexity and lexical properties. So better correlation with fixation duration at the baseline, right? And fixation duration has been associated with lexical properties, right, in prior work also. So that's pretty straightforward. That's pretty clear. Now, scan path complexity and readability, except for FK readability score, our supervised CACOM measures and captures the notion of reading is better. Now, FK readability is biased towards lexical properties. right? And that's why it does quite well. If you look at the syntax properties, the saccadic attributes makes SCACOP a better thing, right? And that's also quite like evident from the prior literature. And here it's very clear. The moment you go beyond lexical complexity, our stuff is a lot better. This scan path, discourse, etc., etc. So the score reference was again better in our case, though not a lot better. The significance value was relatively lesser, but still it was better. And if you look at the scan path complexity with the general of discourse connector, their count, etc., that is actually significantly better. And discourse connectors may increase the need of revisiting the constituent discourse segments, thereby increasing regressive saccades, right? So that's perhaps well captured by our scan path complexity models. Because obviously the moment you have more regressive saccades, then that by itself is pretty interesting actually. That's the summary of this paper. Again, I'll take a pause here. I hope it's clear enough, and obviously there are like 3 more papers to cover, and I'll probably wrap up in another maximum 40 minutes so that we have enough time for question answer. I'll try to keep it shorter. We will wrap up in what is it? It's 8 past 11, so I'll probably try to wrap up in another 32 minutes. 37 minutes. So any question here, or should I just carry on? I'll again pause for a few seconds.
No more question. You can carry on.
Perfect. So let me carry on. So the next couple of papers, actually, if you look at the next 2 papers, I'll almost combine them into one because I don't have too much time left. This is a very interesting topic, so I have to digress a little, even though it's an NLP kind of session it's supposed to be. But there are a lot of other problems that I thought are interesting, and who knows, you might actually be able to form like related problems, NLP problems, or people who are from multidisciplinary research interests, they might find interest. So I thought I'll take the digression. So I'm a little out of time to cover all the 3 papers, but the second and third, which is CoNL 2016 and SEL 2016, those are very related, so I'll probably take them together and present them together. And by the way, I said this as 2018. What I meant is 2017, right? So I'm sorry for that, but yeah. Anyway, so to come here, what I'll do is I'll cover the sentiment analysis paper in depth. The sarcasm detection paper is exactly similar, except it's on a different kind of data set. So once you read one, the other one will be quite straightforward. So what is sentiment analysis? We all know, right? Let me still repeat once, but we all know. It's automatically detecting the sentiment polarity as positive versus negative of user-generated short lists and sentences, right? For example, if you look at this thing, the Shawshank Redemption is one of the best movies I have ever watched, which is a positive way in the ACs we see. The background of this research, as you probably mostly know, right? It's a deep research that has happened over the last couple of decades. Infinite number of papers in the area. Very difficult to beat the state of the art. I mean, deep learning did improve it, but that's a different story. Very recently, so this work we had done back in 2016, early 2016 actually, right? So that's when deep learning was just coming up. So anyway, and the supervised approaches having bag of this thing, right, and then property-based stuff. And there's some deep learning stuff that has happened, right? Some CNN and learning-based stuff that has happened, right? And that has been like anyway. So that's why it is now. Why do you need that? What are the new approaches that you need, right? Okay, look at some of the sentences. Implicit sentiment. If you look at this is like a movie thing. Guy gets girl, guy loses girl, or he is falls asleep. Somebody says this, right? And you can make out it's like the sentiment is like it's dull and boring kind of. This sarcasm and irony. This is an example I was giving. Then it's a kind of movie you go because the theater has air conditioning or whatever. Then that's actually sarcastic. That's not a reason you go to a movie. Then there's a question of thwarted expectations, right? The acting is fine. The action sequences are top notch, but still, I consider it as a below average movie due to its poor storyline. So you start positive. The acting is fine. The action sequences, they're top notch, but it's a below average movie because the storyline is not good enough. But the existing works, they leverage hashtags, stylistic things like lol, and maybe some at most some sort of like practical issue like DVPedia, etc., eBay, Wikipedia, those sorts, right? Which are real life dictionaries. But the moment you have explicit cues from readers, that gives a very strong indication of what it can be, right? And that's what this work attempts to do. So what's our approach? Sorry, we derive and augment cognitive features with traditional textual features, right, to perform feature-based classification. Why eye tracking? because textual nuances affect gaze, right? And nothing but eye tracking to better capture that. Then the feasibility. It's becoming more and more feasible, right? Nowadays, you have handheld gadgets like mobiles. You don't really have to go somewhere and see, this thing becomes valuable when everybody can use it, right? So if a user tomorrow starts giving you permission to switch on the, let's say, the camera, mobile phone camera on a private mode, for example, right, and then really process your stuff locally at your backend, so locally at your front end, right, and doesn't even send your information to the backend, and if there's an auditable way to prove that, right, so let's say something called something like a blockchain or whatever. So if the user can actually prove that, it accustomed and customized for me locally without sending my data to a backend, but using the camera by local processing, I'm pretty sure there's going to be a lot more adaptation to this. Right? So yeah, there's a lot more potential. Achha, now, okay, so if you look at this thing again, sentiment, annotation, and eye movement, and that's for sarcasm also. Look at the red ones versus black ones. And on the x-axis, think of the position of the word in a sentence, and at the y-axis, think of a timestamp, like not timestamp, but an instance T1, T2, T3, whatever, right? So sentence 1 is, I'll always cherish the original misconception I had of you. If you look at the data from 3 different readers that we had captured, they all have this thing. They read it and then they go back and forth, right? So that's pretty interesting, because anyway, very obvious, right? Because you don't cherish a misconception. So there's a flip somewhere. Something has changed over the sentence. And if you look at the second sentence, the lead actress is terrible, and I cannot be convinced she is supposed to be some forensic genius. Now, if you look at the reading pattern of 3 readers, it was mostly linear. Sure, the third one had a long jump at the end, but they never came back, so it could even be an error, right? Very likely. And if you see there are a couple of back and forths in the middle, which is fine. Sometimes it's hardware issues, sometimes it's just a one word here and there that is. But if you look, contrast the 2 sentences, the longer sentence, which could have been lexically more complex, has a really linear reading, but even the shorter sentence has much more back and forth. So it's not about the sentence length. There's something more to this, right? And we are using that more to do the sentiment annotation here. So the first one, as I said, right, is sarcastic. So there's longer fixations, multiple occurs. Second one doesn't have that, right? So we use 2 publicly available data sets released by Mr. Etal. Mr. Etal being Avijit Mishra, who was the PhD student in this work, right? So the data, the data attributes are given here. We have 7 annotators for the first one, 5 for the second one. Right? So I'll just move on. So there are different kinds of features that we look at. One obviously is standard textual feature for sentiment analysis. I mean, we are pretty much in a state of the art or whatever, because the state of the art for this without deep learning has not moved much. So whether if I go back, the 4th paper I present will actually have deep learning into account with eye gaze tracking. So these ones are done slightly ahead. So these ones didn't have any kind of deep learning, more of feature based, but had eye gaze tracking. Then we had a deep learning paper also, which uses eye gaze of users over the words and the actual reading, right? The actual reading patterns of the words, right? I mean, sorry, the actual text, right? So the combination of the 2. I do have that paper, and that's in 2017. Then if you look at the sentiment analysis, this thing, so there's this. These are some of the good papers. We took these features. Aditya Joshi et al. Again was an IIT Bombay student of Pushpa Bhattacharya, and he was his colleague there. He was doing his PhD while he took this. So, and Ramtek, I suppose, will be Rahul Ramtek. I'm not too sure. It should be Rahul Ramtek. I don't recall. So anyway, there's the presence of implicit incongruous presence. Then longest positive negative subsequence, right? And punctuations and interjections, right? So those are things which were for the sentiment analysis part. And then, yeah, then the simple. So the cognitive features, which is a simple features from eye movement. So there was this average fast fixation duration, which I explained earlier. The faster we look at some word and for each of the words, average fixation count, average suckered length. And by the way, I'm not going into these terms anymore. I'm hoping that they are clear to you by now. If not, then just let me know. I'll re-explain. I'm just doing that in interest of time and based upon what I've covered so far. Then the total regressive suckered count, the number of words skipped, the count of regressive circuits from the second half to the first of the text. So what I mean by this is coverage. What I mean is, if you divide the sentence in, let's say, either two equal halves, or if there's a sentiment flip somewhere. So if you look at sarcasm, for example, there's always a sentiment flip, or there's mostly a sentiment flip, not always, but usually there's a sentiment flip, right? So there's something called incongruity, and there'll be a point of incongruity. Before that incongruity, the sentence will say typically something positive. After the incongruity, the sentence will typically say something negative. Sarcasm is typically this. By the way, you can even have a thwarted expectation, right? If you look at that example that I had a couple of slides back, this one. So again, there's a flip of sentiment. The acting is fine, positive. Action sequences are top notch, great. But still, I consider it to be below average movie due to its post-story. And okay, from very positive, it become a negative thing. So you don't have to be sarcastic all the time. There can be other kind of sentiments, but there can be a flip of sentiment, right? So all of that needs to be captured. So that's why the second half to first half thing is quite interesting. And then the position from the word that the largest regression starts. So what does that mean? That means the reader so far until the largest, typically, again, it's not like a guarantee, but quite often, until the reader realizes something is wrong, they'll keep going forward. Sure, there could be a word here and there, but typically they'll keep going forward. All of a sudden, it hits them in the eye. Oh, what did I miss? Maybe at the end of the sentence, maybe nearly at the end, maybe somewhere in the second half, or whatever. Oh, what did I miss? Then they go back almost to the start of the sentence, or somewhere back enough that their eye and mind wants them to take. They start rereading. Okay, so that's typically a large regression, long regression, and that tends to be quite informative. Then the features for sentiment analysis are as continuous the graph thing, right? So I did mention this once. So what was scan path? Again, for a very short and quick recap, what was scan path? The scan path was somebody would look at a path of the eye gaze movement and the set of the timestamp set of nodes and edges. Here in a saliency graph, you move the timestamps, and if somebody looked at some vertex multiple times, you sum that, you add them up always. If there's a circuit between a pair of edges, between a pair of vertices, if there's an edge between a pair of vertices multiple times in the same direction, or even agnostic of directions, right? Then you can just ignore the direction, sum up all the backward and forward edges, and call that as the edge weight, right? So yeah. Now, edge weight can again be done by that way. So you can call it a single edge. I'm sorry. The edge weight can be done by the fixation duration at two sides or at one side, or the total summation of circuits, and that can be just forward, just regressive, or both. It can be the distance between those two words, and so on and so forth, right? So there are different ways to create edge weights, and you can try one or more. These are the graphs of the words that are salient from the point of view of the processing of the linguistic subtleties, right? So what was important in this? That's what this thing tries to cover. Now, features from the gaze saliency graph. Oh, by the way, that also reminds me something very interesting. I'm sorry, I should have mentioned this earlier, but so long back, very early in today's talk, a couple of videos that I showed, that is two of them, out of the many, two of them, right? One was the multiple people tracking video, and the other one was touchless interface, right? So the intern for that was somebody. He was a BTech student then. He's doing his PhD in CMU right now. But then his advisor from IIIT Guwahati had also taken some part in those things. I mean, it was mostly the intern, but he had also taken part in that. And interestingly, he's also, what I noticed yesterday is he's also going to be a speaker in. I mean, I'm sure he'll talk about a different topic, right? But he's also going to be a speaker in this thing, right? So that was a nice collaboration we had. That's Dr. Firdaus Ahmed Barbuya. We had a very nice collaboration on this work also. It suddenly came back to me that I had seen his name in this panel, right? This 12th to 16th October MDP that's happening right now. He's one of the speakers. I don't know whether it's delivered already or not, but I realized it yesterday when I was looking at the set of panelists. He was a part of the system side of this work. I'm covering the NLP side. He was not in this part. The system side actually is a part of the work. So I thought it's worthwhile mentioning here. Anyway. So, sorry, it's a complete digression, but I just suddenly realized. So I thought, okay, let me mention regardless. Because it's just a small world, So anyway, features from the gaze saliency graph. What are the features that we use from the gaze saliency graph? Edge density, then highest and second highest degree with the fixation durations, right? At the source node and target node as edge weight. And so, so there'll be four things, right? Because there'll be the highest weight, there'll be second highest weight, based on the source node, based on the target node. So there are 4 combinations, right? So those 4 things are these F1H, requests, etc. And then the same thing with the forward circuit, and forward circuit count is one, forward circuit distance is the other, and exactly the same thing as a reverse circuit, right? Both in terms of count and distance, right? So those are the base saliency graph features that we added. Then obviously there is readability things, right? You can, because if the text is not very readable, then it can affect the IGS movement, I think. So here we did the FK thing, right? That I covered in the earlier paper. We use that here. And then the very other straightforward things, right? Average sea level per watt, total watt count, which are a couple of other obvious extensions. We use those. And then what are the guess features? Why simple ones, right? And why the complex ones? Okay, we know why these are, but why the simple ones? Because if there are significant variation in guess attributes, right, then fixation, regression, etc., regression, skip count, and observe text. And when those will happen when the text has a lot of subtleties, right, which can be observed through these tests. And why the complex ones? The moment you have like more complex stuff such as sentiment thwarting, sarcasm, irony, right, then that needs you to understand more than just fixations and regression counts and so on, right? It needs you to understand the workflow graph as a whole, and that's why you need the saliency graph and complex case features. So if you look at the example below, bad company, bad movie, just plain bad. Very simple, very good. But if you look at this thing, Serving Sarah is a little more than a mall movie designed to kill time. This is definitely more complex than the previous sentence, right? So all of that needs to be accounted for. Okay, so I think that probably justifies why and also describes what. Now let's look at the results. What did we do? We had the data set, as I said, right? And we had sentiment polarity prediction of snippets, which is a binary classification problem. Then there are the classifiers, which are the very basic, like well-known classifiers, right? And then we have got a tenfold cross-validation tenfold consolidation evaluation. And what did we do for feature combinations? Purely unigram, then unigram including sentiment including unigram, then state of the art for sarcasm, irony, and sorting features, which includes unigram, etc. also. And then finally grace and readability, which is like our main contribution in the work. Now, how are the results? So if you look at the abbreviation, SR is the sentiment, SR is the sarcasm, and GZ is gaze, right? So you've got sentiment plus gaze, sarcasm. So SR is sarcasm, right? So sarcasm plus gaze, etc. But point is this: whenever you see a GZ, that's when gaze is accounted for. Right? And then if you look at the two tables for the two data sets, if you look at the bolds, apart from a couple of cases in the second data set, it's always like talk of precision, talk of recall, talk of F-score. In the first data set, it's always and by far when you have gaze. And obviously a full-blown version of gaze, right? When you have got the sentiment, sarcasm, everything along with gaze, right? Not just the gaze. And in the second one, apart from just the naive-based method for unigram, whenever you add that up with whenever you add that up with gaze, it does better. But then, if you look at the absolute numbers for naive-based, they are 50%, right? While if you look at what gaze could achieve with SDA, multi neural networks, etc., along with obviously sentiment and sarcasm, the base was is 70%. If you look at the F scores, for example, those are practically 71.8, and so and then the other one is 69.1. Yeah, there it is, 69.1. So even though naive base with gaze is not doing well, but who would use a 50% score when you can actually get 70% accuracy? So it's more for a baseline, and for a practicality, it's just meaningless. You just go for IGS tracking with this thing, right? With all the other sentiment, features, sarcasm features all included. I hope that makes sense. Okay, great. And okay, these are the significances, so that's fine. And if you look at this, more than so if you look at the observation statement below, more than half of the top 20 features are actually cognitive features. Okay, now let me focus back on this. If you look at the pause score, LP, right? So if you look at it, I won't read through this, right? I mean, I just pause for a moment, and if you don't remember something, just let me know. I'll flip a few slides back and help you recall. But if you look at it, majority for both the data sets, if I look at the feature significance, which feature played a main role in getting those results, it's mostly the IGS features, I mean the cognitive features. Okay, excellent. I'll just keep moving. Maybe this has given sufficient time. So sarcasm detection, I'll cover it very fast because it's almost a mirror of the sentiment, except it focuses more on sarcasm. Being stranded in traffic is the best way to start the week. Of course, that's sarcastic, right? So as you can make out. And sarcasm emanates from textual incongruity, which is something I was mentioning before. What's the state of the art? State of the art, again, maybe it's something you can look up because it's not something we have done. So it's probably also well known to people. But yeah, those are the state of the art at the time of doing this, and we are trying to contextualize it through these representations. Features, if you look at it, it's pretty much similar features for sentiment because ultimately sarcasm is a type of sentiment. Sure, it's a very particular type of sentiment, but it's so this is more learning for sarcasm and more creating more features. And then it's exactly the same set of data sets, except we take only the sarcasm part of that. And if you look at the results, whenever you have got BS plus, obviously there's no point of taking sarcasm features as sentiment features in the previous one that you have seen. But the moment you start taking gaze along with sarcasm features, that's when you see the state of the your stuff to be our stuff to be really a lot better than state of the art. It's like quite a bit better. Then I'll give a moment for you to look at these tables, maybe another 30 seconds again, look at these tables because it's very hard to read out. It's much easier to look at, but if you look, it's really good. Okay. So again, it's mostly if you look at these things, it's mostly the complex case factors are playing a major role. So okay, now to come into the deep learning paradigm, I just have 11 minutes to talk through, 11 to maybe maximum 15 minutes to talk through. So I'll keep it very short and simple, right? But yeah, I know I spent some time on the rest of the stuff, but yeah, maybe it's worthwhile. So I'll keep this thing short and simple. Obviously, you are most welcome to read on the paper and know more detail. But if you look at just take a moment outside the talk and look at the historical evolution. If you look at the timing of these works, that's when this deep learning. We had a follow-up work of this also, but I didn't include this. That was in AAA 2018, but I didn't include that here because that would be too much to talk through, and that was a very profound piece of work. So that's also deep learning. But the beauty of that work, which I'm not covering in this talk, is think of it. I'm talking of eye gaze, right? But what if you don't have eye gaze? That's a very interesting problem. You want to use eye gaze, but you don't have eye gaze. What do you do? So it's like, okay, I don't have something I want, but I want to use it. Okay, so I'm not talking of this, but let me give a very brief glance. If you're excited, please feel free to read that paper also. But that's a whole piece of work in itself that would have taken too long, so I didn't include that in this talk. But it was that, okay. So when you have training, so what you can do is give a piece of text. If you know the piece of text that you want to measure upon, and if you want to assess your audience with respect to pieces of text and want to personalize, what you can do is those pieces of text you can first bring to a controlled environment, see how people are reading those texts, and thereby figure out their behavior, their response to reading those pieces of text, right? And then create a model. Then what you do is when people read that text out in the wild, you okay, so the model that you create actually jointly learns two things: the text itself and the eye gaze, right? So it's actually a multitask problem. And then when you go out in the blue and try to do an actual implementation on the ground without eye gaze, you try to apply the multitask model. So it tries to together predict the text, predict and take into account the complexity and type of text, and then based upon the joint learning, how do you expect the eye to have done in that text based upon what you have seen in a controlled environment. So that's really interesting because that's what starts making it more practical. So that was also done when we are in IBM, right? So that's the time when, as I said, right, the PhD student Avijit had moved on to IBM, and that we had done that purely as a part of IBM. But anyway, so harnessing cognitive features for sarcasm detection is the last one. I'm sorry, that's the topic I covered. So learning feature representation for text classification using deep learning networks, right? So that's what I'll cover now. So that was EC 2017. So we try to learn features from gaze sequence, from the fixation duration sequences, gaze and text using deep learning networks. So deep NLs are proven to be good at learning feature for image and text classification tasks, right, which you all know. And here we are using convolutions, so a multi-channel variant, right? So what's a multi-channel variant? In one channel, we keep static embeddings of the text, but the other one actually we include the embedding also as part of the training process. And then there's a gaze, right? There's a gaze channel separately. And for this thing, why do we do CNNs, not an RNN? This is more of patterns for a lot of people, right? So if you look at the I-guess thing, that's like somebody also asked here, can you look at the I-guess patterns? So I-guess thing is not actually, in a way, it's like more naturally model as a pattern, perhaps. I mean, in the other work, we did model, the one that I mentioned for 2018, we did model that as an LSTM there, but to get started, we thought it's better model as a pattern. So we started with that, right? As I said, in the follow-up, we did with LSTM, which is obviously, as you know, a form of RNN, recurrent neural network. So we did do that. And that was a multitask model, so that makes it even more. We did a more follow-up work on that also, but we couldn't get it to the level we wanted, so we never published it. But that was trying to do adversarial learning on exactly the same problem, right? When you have data for many people and in a control situation, but don't have it for the uncontrolled situations. Learning, but that actually could not really improve anything upon the multitask learning. And then eventually, because of the focus, the shift of focus, we could not like explore any further on that. But if anybody wants to pick up, like look at potentials of adversarial learning based upon what we did in 2018, they are most welcome. It's something worthwhile, right? It's a very good challenge. So now, why convolution on neural networks? Okay, so I might really stop me another 7-8 minutes. So let me give it audience here, right? We all know what's embedding. Is that correct, Dr. Farikar? Dr. Fadikar, what I'm asking is, the audience here is like, it's a pure NLP audience, right? I mean, almost the entire audience knows, right? What's embedding. Hello, am I audible? Hello.
Yes, sir, you are audible. You are audible. Hello.
Yeah. Okay. So what I was asking is this audience mostly an NLP audience? Do I assume that word embeddings are understood? Then I can proceed accordingly.
I hope they can understand. I hope they can understand. You can
yeah,
proceed.
fair enough then. Yeah. If majority of the audience has an NLP background, they'll obviously understand it. But yeah. Anyway. Okay. So then, if you know what embeddings are, right? So if you look at this, so there's this text embedding that we have for each of the words that appear in the text, right? So that obviously gives n by k sentence representation of the sentences, right? There are in words and k-sized embeddings. Now completely on a different dimension in terms of number of participants, right? So then we have got different number of participants, right? We've got like 8 participants in our case, right? So we had this as the what do you call it? A participant representation also with respect to a sentence. So obviously you could have now the sentence takes only the words have to be in that order. The catch being the participant orders you could have flipped, right? And we never managed to complete this. We know it's a weakness of the work, but you could have shuffled the participant order and maybe had a different result. I don't know. We never knew. But we tried to create a window out of it and see how things work. And that's probably a reason we eventually moved to LSTMs, right? So anyway, we had a static channel, we had a non-static channel, and then we had like 1D convolution operation with multiple filters and feature maps for the text, and then obviously there's a max pooling done. Okay, so I'm also assuming literacy in deep learning, so that's too much to explain, but I'm just hoping that it's a general machine learning background audience anyway, NLP or not. So I'm hoping deep learning is clear in general, right? So convolution operations, I don't have to explain hopefully. And then 2D convolution operation with multiple filter row and column weights, right? So we tried with different of this thing, and then we max pool this, and then eventually merge the pool values, and eventually, right, we do a fully connected with dropout and softmax, right? So that's the channel. It's a pretty simplistic channel, except note that there's a static channel in the text, but then there's a non-static channel also. As the training process happens, the non-static embeddings are also updated, so the losses are also propagated there. And then the gaze component, again, there's not really much to update. It's more of an input thing, right? So think learns over the non-static channel in a way, and then model gets fine-tuned over that. Right? So then to continue, there is a non-static embedding channel to tuning embeddings for SA, and there's a static embedding channel which will prevent overturning of embeddings due to collocation. Right? And why did we do this sort of a network design? So there's a fixation channel which is lexical complexity, right, which will be pertaining to length, frequency, etc. There's a saccadic channel. There's a saccadic channel, right, because syntactic complexity, incongruity, everything, right? So that's why, because the moment there's saccards, etc., there's a question of movement, and non-static might really help there. And fundamental problem of order participants, which I also mentioned before, you cannot try all the all orders, right? It's like exponential. You just cannot. It's like combinatorial, right? Obviously, you cannot do that. You cannot take a combinatorial order. So you have to, like, the case component is affected by that, but for the timing, we just trained and tested, and like, we just trained and tested with the order constant. Would something change if we change these orders? Maybe they would. We don't know, because we didn't get enough time and enough motivation to follow this up, because this by itself, this was a weakness, and RDNs are perhaps better. So use the same set of data sets, right? Then, yeah, I'll really wrap up fast now. So there's this text attributes, which is text, the static channel, the text non-static channel. Then obviously that makes a text multi-channel where the two inputs merge. And then for gaze, we have these gaze channels, right? I mean, that's pretty obvious, right? We have gaze fixation duration, saccard, multi-channel, and so on and so forth. And then we had 9 configurations over this. Now, word embeddings, we use this, right? As you can see, it's like word to wake with Amazon movie review data, and we use 300 embeddings, 300 size embeddings. And typically, we have found good results with 3 to 4 size filters, right? And number of filters used is 150 typically, right? And hidden neurons is 150, and then it's not better than small values, so it's like better with smaller values. It should have been better with, it's a typo here. We had a 0.25 as a dropout probability where we saw the best results, and typically like 200 epochs of training, it really saturated at the end of, like, near the end. And so these are like a hyperparameters, right? Around things. Now, if I come to the interesting part, result. So if you look at this thing, what happened? So the systems, this thing, the 73.3 is the precision, and this is the recall. So the score is pretty high, right? So this is the prior works, right? And if you look at what we could achieve with this, with the deep learning, so this reference by the very paper that I referred just now. If you look at the fifth row, actually, that's exactly the paper I tried to cover just a little back, like the sentiment analysis numbers are lifted from that paper. Now, since the same data set with our deep learning network with IGES, if you look at the bottom parts and the boldings, so it was typically plus minus, more often than not, it's a 5% kind of improvement that we mostly saw. If you look at the FSOS, it's like 5% improvements over that, right? So on the dataset 1, on dataset 2, it could have improved more, but what was really missing is, sometimes the datasets are too small also to train, right? Because in deep learning, you typically need more data. That was also quite reasonable results, right? I think that's what we had, but the dataset 1 had really strong results, and that's what perhaps got this paper accepted. And then that was the sentiment. And with sarcasm, if you look at this is also like, quite strong. If you look at the F score, for example, it's quite good, right? The state of the art was 85 point something, and this was 86.97. So I think that all of that was pretty good. All of that was pretty good. And the deep, but if you notice this, the deep learning, without a deep learning, our system could take to 75.7, while this was 85. It's 10% better. But the moment I had deep learning into the IGES tracking, again, I think there's a percentage better. So it's like, deep learning with IGES is probably the way to go. I see there's a question. Just give me a moment. No, this library and tools, not really, right? There's no library or tools. Let me just answer live. There's no library or tool that's used for this analysis. We just collect the data and write our own codes to analyze. There's no separate library tool, and these codes were also not released. So since there's an IBM like company component to this, these codes were not released. But then once you have these IGES results, this again, if you look at deep learning, for example, you have a lot of libraries online, right? You can just pretty much go and code up those. So it's not a too hard an effort. This is more of an imagination effort than a coding effort. The coding effort is not too high, but obviously you have to think and be sure that you are coding what you want to code up, and that's the harder part. I hope that answers the questions. Are marking done, but if not, please pick up or type again, please. This to Dr. Pramit Amit Patrachandra. Okay, so thanks a lot for the questions. Oops. And
First up, one of the participants asked question that is it applicable for online examination?
oh yeah, I did answer that. But let me repeat the answer. Yes, it is applicable for online examinations because you can track the participants, the how do you say, the students' head pose at the eye center, and thereby figure out whether they are looking at the screen or elsewhere. Plus, if you also log them with a screen map, and if they have material material they want to copy from as a different window on the screen, you might want to augment that the system, right? That they are not copying from elsewhere. But yes, it's very much applicable. Very simply. So there are two ways you can there are two things you can measure. Whether they're looking outside the screen and whether they're looking inside the screen but at a different window. Outside the screen, you can use it at the onset. Inside the screen but at a different window, you might have to combine with some other system that tells what's the front window and at the pixel they're looking at, which is given by a system. What is the window that's present? Is it really the answer screen, or is it some copying material or whatever, etc., etc. If catching cheating is the objective, if you have some other objective, please pick up, because when you say online exam with eye tracking, that's the thing which comes to my mind at least. Okay, great. So any other question or not really?
Any other questions?
Is my screen, sir? My screen share went off. Hold on, sorry.
Sir, am I audible?
Yes, you are audible. My screen share went off. I didn't realize. Please, yeah, please tell me.
Sir, I have one question. That does this device take peripheral vision into account?
Take what into account?
Peripheral vision means we are focusing on the gaze point, and human vision is means based on the field of view. We can view all the.
That's a great question. That's a great question.
Yes, sir.
So look, if you look at okay, there's no single device first of all, right? These are either software systems or hardware. Like that one that I'm showing up, that one has a software system. Now, what it does is it gives you a XY coordinate that you're looking at. That's a pixel, not a field of view. But what you can do is you can always construct an approximate region of view with that, and the software that comes packaged with this system, I think it used to give that, yes, from what I recollect, that okay, this is a field, like not a full field of view because there's no clear definition of that, but what's like very adjacent to that, like adjacent enough to that. But then you might want to also do a little better than just take it on the face, because the field of view itself is a very hard thing to say, and depending upon what you're looking at, the field of view value might change. Depending on semantics of what, and that's also a very interesting question, right? A research question. Like if you look at a simple piece of text, complex piece of text, image, colorful image, black and white image, what happens to your field of view? Like let's say contrast, changing colors. So can you improve or focus your field of view? Right? There's a lot of potential research that can be done on this.
Yes, sir.
Okay, great.
Okay, thank you.
Anyone has any other questions?
Yeah, let's actually open up for the questions. Yeah. So yeah, let's open up for the questions. We just have 15 minutes left. This theory I've covered. I mean, theory is in the background thing, right? So observations are pretty obvious. Maybe I'll just give a moment for people to read through this rather than trying to talk through. And at that time the others can also start asking questions. So I can start answering in parallel. If not, then I'll keep talking more.
Please post your questions on the Q&A chat box. Attendees, do you have any questions?
I think we can proceed now.
Yes, sir.
Okay, sounds good. Sounds good. Sure. Okay, so okay, then let me go through the slide, right? Since I have time, let me go through the slide more comfortably. So overfitting for essay for dataset 2, the training accuracy reaches 100 within 25 epochs. With validation accuracy around 50%, right? So we can probably have a better regularization or dropout to avoid any kind of overfitting. And dataset 2, I think that's the whole reason that it didn't perform as well as dataset 1. We had the same, we had the same model, but the training level was different. And that's actually a typical catch with deep learning systems. Unless it's like you know how much, if it's not enough data, then you have to know how much you have to do to avoid the overfitting, which you all know. Then better classifications for for sarcasm detection, right? You can always obviously do better on that. Then there we might actually we have like tried to reduce the dimension a little bit and seen some improvement. So there might be some scope to do there, but definitely have seen some already. Then if you have too many convolution filters, the accuracy was going down, so you have to stop at a point. Okay, so the peak is somewhere between 30 to 180, and we eventually reported with 150 types. And the effect of static and non-static text channel. So mirror for non-static with 1 sentiment, since since like mirror sentiments can come closer, right, in a way. Like good and nice, for example, they can come closer in non-static channel. Effect of fixation on Saccard channel. Saccard channel alone can hear nuances like incongruity. There the fixation doesn't seem to help much, because fixation duration might change and so on, and that doesn't really have to have things like incongruity, but obviously overall it helps. So to carry on, so we'd like to, so analysis or features that are learned, we'd like to, so if you look at this thing, so how did multi-channel do? So for each of the sentences, we look at there are 4 sentences that we are showing, right? I would like to live in Manchester, England. The transition between Manchester and death would be unnoticeable. Now, very clear, it's sarcastic, right? I mean, all they're saying is staying in Manchester is almost as bad as dying, right? That's all they mean. That's all they mean. Sorry. Right. So if you look at this thing, so if you look at the middle of this, right? If you look at the middle of the sentence, the box that has been bolded, that's where the real thing is. Because, and if you look at the sentence also, around the middle of the sentence, transition between Manchester and death, that zone is where the whole sentiment flips, right, in a way. And exactly that's, you can actually have the same thing there also, right? So if you look at that's what makes the problem a little challenging, right? So it's not necessarily an easy problem. So we really did not like this camp. After a disappointing summer, we switched to another camp, and all of us are more happier on all fronts, right? So if you look at similar positions, and if you look at the boldness of the bars, they are not much bolder. They are okay. So there are very focused there, but yeah, I mean, very clearly, if you look at the bar shapes, they are different. And if you look at other kind of non-sarcastic sentences, positive and negative, they are pretty similar, right? So yeah, they're pretty similar. Now, if you look at multi-channel text versus multi-channel gaze, having gaze, if you notice, so if you look at the text, they are uniform versus not. But if you look at the gaze, very clearly, some parts are very salient, has a very pronounced, highlighted when you use gaze, and that's what makes the analysis better, right? And that's why these models are at all giving good results. So if you look at these things, so if you look at the arrow, if you look at this arrow, the capturing of intensity varies with sarcasm versus no sarcasm is definitely better, right? If you look at the 2 arrows, and if you look at the intensity in the sense of the thickness of the bars, first one is sarcastic, second one is not, and I'm sure you clearly see the difference, right? And more so if you compare with how the phrases happen in the other words of the same sentence. I mean, you look at it horizontally, take this pair, look at each of these sentences horizontally, left to right, compare the 2 sentences vertically along each other, and particularly compare those 2 boxes, and very obvious that they're different. Right. Okay. So analysis of learned features is addition of gaze information that helps generate features with subtle differences. Features for non-sarcastic that exhibit more intensity than the non-sarcastic ones. And the example 4 is actually like correctly classified by both the sentences right here, which might be simply a lack of context. But anyway, so I think let's not worry about that, because obviously in absence of context, there's only so much you can do, and you have to live with that, right? Now I think that's pretty much it. Here are some examples of patterns that we had, not just for NLP, but in general for the area. I mean, I think there are like 15, 16 patterns that we had in this area, because the area obviously is huge, right? All the way of applications, like I said, this like the one that I said there, the way of, like, for example, like moving planes, for example, right? How does some stuff move, and then how does the human eye react to that? How can you like reorient? Because remember, when you're conducting a XY thing, your head is related to the camera, right? So there's a question of calibrating where you are looking at. That's called calibration. So how to recalibrate automatically? So you make out that your head is at that distance, eyes at that distance, that angle, head is at that angle. So what does that translate to with respect to the screen, with respect to its current orientation, right? So all of that, for example, right? So we have a lot of like stuff in this area, all of these areas. And if you look at the first one, that's purely in the NLP space of these 3 patents that I have exemplified. Memory augmented factoid question answering influenced by human gaze behavior and text metadata. Right. So there are all kinds of things really. And this is just a set of references that are additional work for the area. Let's not go into this. So let me stop sharing my screen now. And if there are questions anymore, then we can take that. Otherwise, we'll start wrapping up.
So any question from the participants? I think, sir, you have already answered all the questions. So no more questions today.
Thank you. Yeah, and I hope it was not because like I was talking too fast, because I have a tendency of talking fast and people could not follow me. I hope that's not the case. If somebody didn't follow me, just let me know, please. If there's some particular part that might not be a question, just pointing out to one of my weaknesses, but that's perfectly fine.
Okay, so I'm repeating again. If you have any questions, attendees, you can post your questions in the question and answer box.
Okay, that's it. I'll pause for 30 seconds and then wrap up with a few concluding remarks and then hand it over. Just pause a few moments just in case there's something. And yeah, seems there is not. So okay. So first of all, right now, as I said, I'm not really pursuing this work. IIT Bombay might be separately pursuing right now. I'm not, like they are probably, but anyway. But if any of you really want to pursue any of this, it's a very exciting area, and as you say, it's not just NLP. There are other areas. B, if if anybody feels that I can be of value, then feel free to reach out. That's there, right? I'll be most happy to do that. And but for reaching out, obviously, Dr. Farikar has my email address, right? My personal email address. He has my phone number also. So Dr. Farikar can definitely share, and Dr. Farikar, you're welcome to share if needed. And otherwise, also you should it's one of the areas that's very promising. So if it's anywhere close to your area of interest, feel free. And if somebody has an access to, let's say, EEG kind of stuff that they can fit on the participants and collect etc. from, that's also a direction I would love to pursue. So if somebody invites me to that kind of a research, I cannot do it right now because of my professional commitments. I mean, not as part of my professional commitments, but in parallel, I can always pursue that also. So that's also an open area of potential collaboration also. I think that's it for now. Okay, I see there are a couple of, again, something has wrapped up as the question answer. Okay, thank you. No, great.
Okay, I'll ask Kaushik.
Yes. So there are no more questions. What I can see. Thank you, Dr. Dev, for your enlightening and informative presentation. It was really a nice learning experience for all of us. And we are sure the participants will be immensely benefited. And we are sure that you'll be with us again in future in some of the other sessions, and hopefully we'll be doing some collaborative works also. Thank you again, sir, for taking time out of your busy schedule. Thank you.
Thank you, sir. Thanks a lot, Dr. Majumdar. So it's very nice to be talking to people, and I also really enjoyed this. So, and thanks to Dr. Farikar for everything. Okay, thanks everybody. So I'll be signing off for now. Thanks everybody. Thank you, Dr. Farikar. Thank you. Okay, thank you.
Thank you.
I'm signing off.
Okay. So we are now going to start the second technical session for the day. And today we have with us eminent speaker, Dr. Bidut Patra from the Department of Computer Science and Engineering. Dr. Fadikar, has Dr. Patra signed in? Or should we wait?
No, sir, till now, sir has not joined.
So we'll be waiting for him. Once he joins, we'll start the second session.
Yeah. For 5 minutes, wait for 5 minutes. Hello.
Yes,
okay, we can wait for 5 minutes because.
Okay, we'll wait for 5 minutes and then start the second session.
Kaushik sir, Patra sir has joined.
Okay. Okay, so we are going to start second session of the day. Today we have with us eminent speaker Dr. Bidut Patra from Department of Computer Science and Engineering, National Institute of Technology, Rourkela. Sir, on behalf of the Department of Computer Science and Engineering, Maulana Abul Kalam Azad University of Technology, West Bengal, we welcome you to this event. Now, it is a pleasure to introduce our guest speaker. Dr. Patra is a faculty member in the Department of Computer Science and Engineering, National Institute of Technology, Rourkela. He has earned his PhD degree in Computer Science and Engineering from IIT Guwahati under the supervision of Professor Sukumar Nandi. He received ERCIM Marie Curie Fellowship from European Research Consortium for Informatics and Mathematics, France, for doing postdoctoral research at VTT Technical Research Center of Finland. His research interests include data mining, machine learning, anomaly detection, recommender system, and educational technology. So may I take this opportunity to welcome you, sir, to deliver your speech on the topic application of machine learning in recommender system. Sir.
Okay, thank you, Dr. Kaushik Mujumdar. I am sharing my screen, and before that, telling about anything, I must be thankful to organizer, especially Santanu. He called me many times. It is really privilege. This is my privilege to be associated with the university. And now I start my talk here. So hopefully you can see my screen.
Yes, sir.
Is it okay?
It is visible, sir.
Yes, it's visible.
Yes, sir. It's perfectly open.
Can you switch off my video? I think I could not find.
You can turn off the video, sir. There is a link at the bottom of your screen. Bottom left.
Yeah.
Yeah.
I am done. So my topic is on application of recommender system, but intentionally I kept the topic recent trend in the recommender system. So maybe we'll talk very recent advancement in recommender system in this talk. So outline of my talk is introduction, and then different type of recommender system, and then recent trend on recommender system, especially the streaming recommender system and the session-based recommender system, and then finally I end my talk with talking what really we are doing at Intelligent Data Analysis Lab NIT Rourkela. So I am moving the slide. Hopefully you can see the slide. I am on the slide number 2. So here I am in the slide number 3. Is it okay? Can you see my slide?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Yeah, thank you. So there is something called information overload. You can see the many device here, especially this is a headphone, and we have that huge number and with different specification. It is really problem to choose the right headphone for me. So this is something called we have the huge information, but we don't know, we are hesitant to take a right decision. This is something called information overload. So information overload is a scenario where the consumer are unable to take right decision on a product due to too much of the available information. So to cope with this problem or that information overload, we have the recommender system. So recommender system basically help people cope with the information overload problem in this digital era. As you can see, and then everyone is experienced with online shopping. In that case, what we see, especially for Amazon or recently in Flipkart, we see the different kind of recommendation. So therefore, the huge application of recommender system in different area. So here I gave few example here. So application area is movie, obviously movie recommender system, and of late that is OTT platform, that is streaming platform. We have the Netflix, even Hoichoi.tv. These recommender system could be used for recommending the movies or any sort serial and so on. So even the people started using the recommender system in e-learning domain. E-learning domain, even of late that course area also started providing recommendation. And then obviously we have the Netflix, and then we have the Amazon, and then Flipkart and so on. So obviously some few application, Amazon, Netflix, YouTube, and then we have the trip advisor and so on. For they have been using recommender system from long time. Even the Netflix, they started use as in the early of this century. So here I will spend some little time to understand what are the different type of recommender systems are there, and based on the input given to the recommender system. So we have the, as I can move here, we have the user profiles. First we understand this row here, what is this? We have the user profile and then item profile. What is user profile here? So in earlier days recommender system, so one has to register with the system. In a sense, user should provide the information about the user. So let's say where from I am, what is my occupation, and then how old I am, and so on. And similarly, items should have also the information, what is the color of the item, and then what is the which category this item belong, and so on. These are the information based on the content they used to derive this type of tables. And then on the other hand, present recommender system solely depend on the rating. So everyone has the experience after purchasing any product from the Amazon or the Flipkart, they ask for, can you give the recommended, can you give the rating? So this is all about. So users are giving ratings on the different items and so on between the scale from 1 to 5. If there is a blank, it indicates that user did not purchase this item. And then of late people started giving the review also. It's not sufficient, rating is not sufficient, and people started giving review on the product. So this is all about. Now based on the information available, so that different type of recommender system have been developed over the decade. So first initial recommender system, only they use the information user profile and item profile. So that type of recommender system is something called the content based recommender system. Essentially, this type of recommender system basically matches the user profile with the item profile, and then top items are recommended to the users. So it has the different, it has the drawbacks. In a sense, let's say in many applications, it is really difficult to get the appropriate the item profile. Let's say if I watch particular movie and particular short-term movies and short film and so on, so it is really difficult to give the user so item profile. And for many multimedia applications, it's really difficult to extract the exact feature of the content of the product. On the other hand, many users will be very reluctant to give the information, especially the age and then say occupation and so on. So therefore, these type of recommender systems are nowadays hardly used. Okay, so now most popular type of recommender system is collaborative filtering, which basically address the problem of not all, many problem of the content-based recommender system. But obviously, content-based recommender system is really good in some scenario where the content-based is only the solution. So in case of the collaborative filtering, as we know, we should get the information from the rating data set, and of late people started using the information from the review data set. And then hybrid recommender system is something, it should take the information from the content as well as the rating and then a review data set. So this is another category of recommender system, is called the hybrid recommender system. Essentially, all these three recommender system basically predict the rating for the unseen or unconsumed or non-purchased item, and they rank those set of items, and then top 10 items are recommended to the users. So I'll more focus on this collaborative filtering. This is really popular, and in 2003 one article says that Amazon they use the item-based collaborative filtering. Even the 2003 is quite old, but nowadays it is really difficult to know that what type of recommender system they really use in the Amazon. So having said that, we more focus on the collaborative filtering. In the next slide, we will see. So here I invest more time here also. So there are collaborative filtering can be divided into two major categories. One is neighborhood based approach, and another is the model based approach. So here we talk about the neighborhood based approach. And then we are aware of concept the neighborhood, because neighborhood based approach used in classification and then clustering approach also. So here also we use the neighborhood approach but in different angle, from different viewpoint. So let's say we first talk about the user-based collaborative filtering. This algorithm was introduced in 1994 from the MIT by Resnick. So this algorithm is so simple. So see, we have the set of user here and we have the set of item on the right side. And there are few dark line from the user to item. This dark line indicates that this girl or this lady, she has consumed this set of items, and then there is another arrow you can see from the item to user. So that indicates whether this item can be recommended to the user or not. So that we need to find using the user-based collaborative filtering. Essentially, user-based collaborative filtering basically find the neighbors of the user, and then it recommend the item to the active user for which we want to find the recommendation based on the taste of the neighbors. So therefore, if we want to find the recommendation for this guy, then what we do, we see what are the item consumed by these users, not only that, and then we see what are those items consumed by the other user. So if you see, this guy has consumed the item, this strawberry and then pumpkin. Okay, these two items also consumed by the first lady. So therefore, what we can see, what are the, maybe this guy has the friend, the first lady, and then we can see what are the item consumed by this lady. So the item consumed by this lady along with these two are the grapes and then the orange. So therefore, these two items can be recommended to the last user. So this is the part of the user-based collaborative filtering. I will tell you more detail in the next slide. So now we move to on the right side, that is the item-based collaborative filtering. So item-based collaborative filtering was introduced in 2003 by Server from University of Minnesota. So here, essentially, instead of computing the user neighbor, ideally they compute the items neighbor. So in a sense, first we check this guy has consumed what are the items. So this guy has consumed item is the pumpkin. So therefore, what we do it, what are the unconsumed item in the set? So for him, unconsumed item are grapes and the orange. Then we compute the similarity from the unconsumed item to the consumed item of the user. So for in this example, whether these item will be referred or recommended to this guy, or this item will be recommended to this guy. In that case, what we do it, we compute the similarity from this pumpkin to the grapes and pumpkin to the orange, and whichever is closest, that item will be recommended to the guy. So this is this is all about the item-based collaborative filtering. So in the next slide, we go in little more detail. See here. User-based, essentially, user-based collaborative filtering or any collaborative filtering must have a table which basically tells about the users and then items, user, what are the items he has consumed and what are the ratings he or she gave. So this is user U1 has given rating 5, 4, 1 over the item I1, I3 and I4. So this is nothing blank, means we assume this is 0. 0 indicate that item is not consumed by the user U1. Now what we want to do, we want to recommend for the user U4. As you can see, there are only 2 items which he or she did not consume. Obviously the item which already have been consumed by the user U4 we cannot recommend, because he has the knowledge whether that item is good or bad. So therefore, we only recommend the item which are not consumed by the user U4. In this example, item I4 and I5. Let's say item I4 and I5, I want to recommend the item which one is more close to his taste. Then what we do, first step is find the similar user of the active user. of U4 who rated the target item. That means first what we see, the item for which we want to predict the rating. First we predict the rating and choose the least best one. So therefore I want to predict the rating for I4. So I will see what are the other user they rated the item I4. So in this example we see all other user U1, U2, U3 and U5 they rated the item. Okay, and then among the 4 items we see who are the closest user U4 or who are the k nearest neighbor user. So there may be the scenario that we must choose the k nearest neighbor user. So k nearest neighbor, for computing the k nearest neighbor, we should have notion of similarity. So find the similar user of the active user. That is active user here. Active user is nothing but the U4, and then we compute the similarity. And once we know that out of the 4, say we want to consider k equal to 2, where k is the k nearest is k value is 2. So we take, let's say, example that 2 nearest neighbor. So 2 nearest neighbor, once we identify that U2 and U3 are the nearest neighbor, then we take the aggregate value of 3 and 4. So we can take the average, that is say 3.5. Or to best way to do this one is the rating prediction. What is the rating prediction for this point? What is the average rating of this guy? So that is RU. And then what you do is for the other rating, how much deviate from the other rating from the other user's rating, the user mean. So therefore, so this user mean will be how much? 3.33. So therefore, rating 1 minus 3.33. And because the similarity is weighted sum, because if the user is far away, even though it's nearest neighbor, so that should be multiplied. So that will give you the total, and then what you do it, we normalize this pair. So that will give you the rating for the I4. Similarly, we compute the rating for I5. If there are some other unrated item, we'll compute the rating for the all unrated item. And then out of the unrated item, wherever the rating is maximum, we choose those items. So item I4 is recommended to user E4 if the predicted rating value is greater than the threshold. Obviously, if the rating value is 0.1 or 1, we should not recommend because highest value is 5. So 5 indicates that is the good item for the user U4. Similarly, for item-based collaborative filtering, we'll do the same thing. So let's say we'll check whether item I4 can be recommended to U4 or not. So what you do it, I said, one needs to compute the similarity between the unconsumed item with the all consumed item. So we compute the similarity between I4 with all these values and then I5 with all these values, and then we take the aggregate rating for those set of items. So this is here we compute. So these are the two major and popular what is called is neighborhood based algorithm for in the collaborative framework. So there are other yes. I said in the last slide key there should be a notion of similarity for computing nearest neighbor. So widely used similarity measures for user based is the Pearson correlation, that is, and then MAKAUT is also used for item based and user based. So MAKAUT is introduced in 1889 around. So there should be a cardinality, this intersection divided by the union of those set of item rated by the individual users. So IU is the set of item rated by the user U, and similarly for B. And then 2003, they introduced that solver in the paper of item-based collaborative filtering. They introduced a similarity measure, so that is something called adjusted cosine similarity. So if you remove this minus RU, so that come under similarly for down, so that shows the cosine similarity. So differ from the cosine similarity to adjusted cosine similarity is something like that. See, if there are some teachers, they are very strict, and some teachers, they are quite liberal for giving marks. Therefore, so it is really difficult to understand the student marks based on the obtained marks from a particular or two different subjects. To remove this biasness, adjusted cosine they introduce whenever we talk about the user rating. So we see it how much more on the user own average. So that is talking about RU minus RU bar. So we will talk about more on this user mean, and so on in the later slide if time permits. So this is something that adjusted cosine similarity. These are the similarity measures are used in case of the neighborhood based and item based collaborative filtering. And people also started introduce many similarity measure, but that become now is little bit old technique for coming up with a new similarity measure. There are quite good number of work in this direction. So now another work is another category of collaborative filtering is called the model-based approach. So model-based approach is one work was introduced in Siam Conference on Data Mining in 2005. That is the slope one predictor. So this is simple algorithm, but really it has a quite good citation is over 1,000 over the time. So here we go. So say user U1 has rating for the item I is 1 and for other item is 1.5. On the other hand, user B on the same set of item has the rating 2, and can you predict the rating for the item J of for user B on the item J? So this is something called the slope one algorithm. What essentially they did, see what is the difference from the rating from J to I. So they computed, and similarly they are assuming that same rating difference will be continue for the other users, and here is rating difference is 0.5, and then therefore these difference will continue for the user B, and therefore rating will be 2.5. So this is all about the slope one predictor. So now is main algorithm what they did it, they compute the deviation for the set of items. Say suppose I want to compute the deviation for item J to item I. So they computed the all values. Obviously we don't know the values here, we need to compute. So we have to exclude this value, but we have the rating for all other items. So there we compute the deviation. See, here we go. We compute the deviation between the item I to J. So then we compute the rating on the item I and the rating on the item J, and then number of user rated both the item. Obviously here this user rated only one item, so we should not include this type of user. So user rated both the item and we compute the deviation. Now when we talk about what should be the rating for this point, essentially what they compute the deviation for this unrated item to the all rated item by the same user, because this set of this computation should be done for the all pair of items. So therefore item J with item I, if this guy has rated some other item, so item J with item K, item J with item L, and then they add all this deviation value here, and then divided by the number of item rated by the user U, and then what is the his average rating. So that gives basically the item prediction value, and then as I told earlier, for each item, for each unrated item, they computed this prediction and they picked the top in item for the recommendation. There are variation of this model-based approach is slope one predictor, and then there is variation of something on bipolar, the different bipolar approach. Maybe this is another variation. So whether the item or light item rating is given light or dislike. Okay. So really very popular after 2009. After 2009, because in 2006 Netflix announced a prize. A competition is something called Netflix prize competition, and that becomes so popular that this guy they won this prize, and that become later on a very standard approach for metric factorization. Metric factorization is quite complex. It is more mathematics than the intuitiveness. Advantage over earlier algorithm for metric factorization is that it gives much better accuracy than the neighborhood-based approach. But neighborhood-based approach is quite intuitive. I like that item because my friend liked that item. So that is the main basic idea for the neighborhood-based approach. But metric factorization is not intuitive. It cannot explain why this item will be recommended. Okay. So how it works? So basically, we have the matrix here, and then there are many zeros as you can see here. essentially this matrix will be divided into two lower dimension, lower and matrix. So here in this example, what we can do it, we can divide this matrix into two other matrix. So that is here dimension of this matrix is, as you can see, so 5 users. So and then features will be 3. Here for item also will have the 3 features, and then once we multiply these two matrix, we will get the original matrix. So that is the idea here. But how it start working? Initially, we put these two matrix with some random value between 0 to 5, 0 to 1, and then we keep on improving the value, one objective function that I will tell you later. Now, before going into in details of mathematics, what we do is once we get at the end of the day, what we get, we'll get these two matrix, and these two matrix essentially gives the feature, latent feature of the users and latent feature of the item. Now, what we want to do, suppose we want to predict, because this is unknown, unrated item, so to give the rating, to recommendation to user U2, essentially we need to find the rating for the two unrated item that I said earlier. So therefore, while I want to give, while computing the rating for this position, that is user 2 item 4, what you do, we do the multiplication. Suppose user 2, what are the features? User 2 has these three features, and item 4 has 3 features. Simply we multiply it. So therefore, any place prediction will be just multiplication of these user features and the item features. And here we go. We essentially we compute this matrix object. Our objective function will come in the next. But essentially, what we do in case of the matrix factorization, so we are placing the user and item in the same features. So let's say if I like the drama movie, so there may be some features that dramatic, and then how much good in dramatic for particular movie, and then how much I like. So that this dramatic, if drama is one feature, how much I contribute in the drama features, and similarly particular product also contribute. And then essentially we compare these two, item and user on the same space. So this is the main idea of the matrix factorization. So here is the objective function. Essentially, these are the ratings given in the what is called in the training data set. That means wherever there is no 0, this is RU, and then we are predicting at the same place because we know the value, and then we are predicting using the value PI and Q, and then we try to minimize this error. And then sometime we know that see, Titanic movie always get the high rating, right? So therefore, and then as I said earlier, also some users are very strict for giving rating, and some users are liberal user. To capture this one, so these other two are introduced, something called item item bias and then user bias. So now we'll talk about some, how much time I have. Yeah, I have another 30 minutes. Okay, I think I'm going in right speed. I don't know whether I am fast or slow. So I have the okay. Then some important area recommender system I will talk about. This whatever I earlier said, these are the what is called is traditional algorithm. Those are not very recent. As I said, 2003, 1994, and 2009, and so on. There are some problem in recommender system, and that we'll talk now. There is something called long tail item recommendation. So item which receive very few rating, and there is something called 80%, 20% rating. That means if any data set you see, or any scenario in especially e-commerce domain, what we observe, see 80% ratings received by 20% of the total item. In other way, in other word, suppose I have 100 item in a store. Say we'll see that 80% of the total rating, there may be, so we have 1000 rating, Okay, 100 items and then the item 100 users. Okay, so out of the say total 1000 rating, so it may happen 800 rating received by the 20% of the item. And on the other hand, 20% of the total item received, rating received by the 80% of the items. So this is something called 20%, 80%. So in that case, what we see, many items receive very less rating. And present day recommender system, basically they are really biased to the recommender system. They are biased to the items which receive mini rating. That means the information which item will have many more information, present day recommender system, they will recommend those items only. Therefore, the item which receive less number of rating, they will hardly recommend. They will hardly be recommended to the user. So this scenario is something called long tail item recommendation. There is another scenario is the cold start user and item recommendation that I will tell in more details. And then diversity. So present day recommender system, most of the recommender system, they focus on accuracy. So accuracy is in other way around is directly linked with the similar kind of item. So, but see, once I purchase one headphone or once I purchase one iPhone or one phone, okay, smartphone, if the system recommend me the another phone, that is not much useful for me. Okay, so if it recommends something different from the from the phone, but my taste is quite okay with the different item. In that case, I will be very much satisfied with that type of recommendation. So in essentially, I wanted to say that recommender system, whatever they recommend, it should have the diverse set of range, the diverse set of item. It is not always it will recommend the electronics item. They may sometimes recommend the some different novel written by the Tagore and someone else. So therefore, based on my the preferences, recommender system should do. So that is something called the diversity. And then another coming up area is the group recommender system that is really used for the when we go for the touring for tour. Very often we like to go more than 1-2 families. So therefore, in that scenario, can recommender system really help us for identify the places where should we visit, where which restaurant might be good for a group of people, or maybe the students wants to go for the movie or theater. Can the recommender system really help us to give some recommendation in that direction? So that is something called the group recommendation. And then recommender system in social media. So social media, we see ki there is something called location based social media, or even the Facebook has Facebook places. So if I visit a new place, let's say the Paris is new for me, I am very much habituated with the locations and other point of interest restaurants in Kolkata, but I am new in the Paris. Can the recommender system really help me knowing the information in my home city? Can recommender system recommend a good restaurant for me? So this is something called different angle how recommender system could be used in the social media. And let another research direction would be streaming recommender system. So streaming recommender system is something is present day recommender system. Whatever I talk about the item based, user based, matrix factorization, they work on the historical data. In a sense, ki 2-3 months before whatever the my preferences, so they use some algorithm like computed the similarity using one of the similarity measure I told, or maybe new similarity measures, and whatever the information they have, those are the quite old 2-3 months old information. Based on that, they are recommending. So this may not be accepted in many scenario, because see, if one product might be purchased from the different part of the world in Amazon store, so therefore that product's rating is getting changed, and whatever it was there in 2-3 months before, it is not now in the same set of the product. And then another essential part is key, user taste also changes over time. So can the recommender system really really incorporate this all information, and they should change the preferences of user on fly. Whenever I change, there is a change in rating that should be reflected in user preferences and recommendation. And then last one is really state of the art. First one started in 2016. So that is something called the session-based recommender system. Basically, here people started using deep learning technique to capture the session. So I'll talk this one also in detail if the time permits. So now I skip that user-based what is called cold start item recommender system. So there are two types: user cold start recommendation. Say I don't know anything about the any recommender system or something. I am new to the Amazon. So then no information will be with the Amazon system about me. So in that sense, in that scenario, can recommender system really help me? So user who recently joined the system. So in that scenario, essentially what they do, they ask where from you, and then those information they implicitly extract and they use it. This is directly related with the what is called is the content-based recommender system. So, and mostly the content-based recommender system, content information is really helpful to address the cold start scenario. Then similarly, one new item they introduce, Amazon introduce in their store, but no one knows about that item. Okay, so in that scenario, how the recommender system should cope up with this type of problem? So that is something called item-based collaborative item cold start scenario. And to address different deep learning techniques or NLP technique, also people started using because I said key content or text informations are available. Those can be exploited for addressing this cold start scenario. Now we talk about streaming recommender system. So in a little more detail. So traditional CF technique, as I said, though efficient, they are not equipped to process the new rating in real time. So as I said, the user taste and interest changes over time in the user preferences. Therefore, user preferences calculated earlier could become obsolete, and that leads to the concept drift. So what is the solution? Solution is that incrementally we need to update the user preferences while there will be new rating. So we immediately update the user preferences as well as the item statistics and so on. This is really a new area, and anyone can work if they are interested, because literature is also few, and not few, it's very few. Okay, so we found the literature 1 year before that we got only 3 to 4 literature in this area published in a reputed conference. So first work was in 2012, introduced in a CIKM, is a ESTA conference. So International Conference on Knowledge and Information and Knowledge Management. So here basically we know that item-based collaborative filtering. So they basically made the item-based collaborative filtering scalable. How they did it? So we know that in 2003 they introduced the adjusted cosine similarity, which is the basic which is the one major contribution in case of the item-based collaborative filtering. So they made it incremental. So therefore, that entire item-based collaborative filtering become incremental. And another conference in 2015, that is SIGMOD, is another top conference, appear in 2015 that 10 cent rate is introduced. 10 cent rate is neighborhood based.
Sir, you're not audible, sir.
Approach.
Yes, sir. Your connectivity, I think, problem is there, sir. Sir, you're not audible. We are not able to hear you, sir.
Any problem?
Sir, we were not able to hear you, sir.
Yes, slide is visible.
Hello?
Sir, your slide is visible, but you're not audible, sir.
Okay, yeah, maybe our
Now it is coming, sir. Now it is coming.
It is
Please
coming
continue,
now.
sir.
Yeah,
Please.
network is not stable in the.
but the voice is low.
Yes. So
Hello. Audible, audible.
so yeah, is it
Yes, it is coming, but somehow a
So it's
break
coming
is
and
there.
going, sir. It's on and off. The mic is on and off, sir.
Yeah, it's breaking.
okay? What is the solution?
Now we can hear again.
Okay. Is it okay? Should
Yeah,
I?
it's okay now.
Yes,
proceed?
yes, yes, sir. Please,
Yes,
sir.
sir.
Please,
Fine, sir.
continue, sir.
So that first work, as I said, in 2012, it is basically they are making the adjusted cosine similarity is incremental. In 2015, in Sigmod paper, they talk about what they did it while computing similarity. The item which are dissimilar, they prune it, so therefore they can compute similarity quite fast. But most recent work, as last year we identified that paper, and then important is again in CIKM by Subayan, and then with Charu Agarwal is quite good name in data mining, and then nowadays in recommender system. So they introduce one. They also everyone targeted on item-based collaborative filtering. How can this item-based collaborative filtering uh, be faster? So the item neighborhood approach which computes the approximate similarity. So locality sensitive hashing is a nice algorithm introduced in 1999 by the Rajiv Motoni and co-author for computing the similarity or computing the nearest neighbor of the unseen object or for a query point. So this is a probabilistic approach for computing the similarity from one point to another point. So they exploited that LSH for computing similarity from one item to another item. So LSH actually can be done in order of constant time. So therefore, they claim that this algorithm is much faster than the other existing algorithm, and result is quite good with compared to the non-incremental algorithm of what is called is item-based collaborative filtering. But all these algorithm, if you observe, they talk about the probabilistic approach. So therefore, there is a high chance that they can miss some of the important item for recommendation. So that is we observe. So we have a contribution in this direction. So we have a contribution in this direction that I'll give you in very quickly. So there is a work appear in ACM Wave, ACM transaction on Wave in 2011. This work is very simple, but this is not used for the streaming scenario. So what we did it, we make this algorithm work in streaming scenario. So that is the contribution. Say essentially we get the user ID and item ID. So and then we have the information user mean and item mean. This algorithm is so simple that it has a quite good citation because algorithm is really simple. So essentially what they did, they computed the user tendency and item tendency. How they computed the user tendency? Let's say for user U1, they computed the user tendency. If you see the formula carefully, what is that? It is computing the deviation from the item mean to the user rating. What is this? So let's say user U1 has rated item 4. So they are saying these rating that is 4, how much it is deviate from these items meeting, not from the user mean. No, item means. So these indicate the item mean. So let's say some movie, okay? So everyone, so let's say Titanic movie. So everyone is given rating close to 4.5 or close to 5 or say 4 or 5. So average will come around say 4.5. See, if someone is very strict user, okay, so if I give the rating is like 3, so that indicates something. So we need to capture this behavior using user tendency. Let's say I am very strict user, okay, so therefore, so my average will be something below 3, okay, and someone is very liberal user, his average will be above some value, say 4.5. So these essence we basically we want to capture using user tendency and item tendency. So user tendency is basically seeing if the items rating is say 4.5 and I am giving the rating is 3, that means it is really the bad item. Okay, so therefore this is this, and then we'll do for the all items. This is something called user tendency. Similarly for item tendency we can do. This algorithm is really good. Is accuracy is at par with the state of the other item based or user based collaborative filtering. Okay, and this is simple algorithm. What we do it, we make it scalable. Okay, so I have another 15 minutes. Okay, so here item tendency as we saw it here. So here, what is the major issue here? Major issue with the item tendency is not personalized. What does it mean? So these item tendency remain unchanged across the users, but it is not possible. Some item I may like in different way, someone else may like in different way. So therefore, we argue that item tendency should be related with the user preferences. So therefore, this this item tendency is not personalized. We made it personalized and then in streaming scenario. That is the contribution here. So what you do, this is very simple algorithm appear in ECIR conference this is the European top conference in information retrieval in 2018 appeared as a short paper. This is very simple. Here item tendency we divide it into two parts and then we analyze it individually how we can update the AU and BU. This is all about our work. So there will be two scenarios that user you rate the new item, then how do you change the rate mean and then how do you change the rating and so on. So another scenario will happen that I already rated but someone is the new, then how I will be affected. So this is that we'll talk about using this equation we computed the user and item tendency. And then what we do it, this is very popular, this is quite same as the what is called is the Jacquard similarity measure. So, but Jacquard is they have taken the union of all. So we have taken the only the liked item and disliked item. And like and dislike basically is identified whether the rating is above the user mean or it is below the user mean. If it is
So we have lost the connection
Yeah,
with
we have
Patru
lost.
sir.
Right. So, wait.
So sir has joined, sir.
is it okay?
Yeah.
Yes,
Sir,
sir.
please
Yeah.
reshare your screen, sir. I think there was no connectivity loss problem. So you were disconnected. Please reshare, sir.
Yeah.
Hello.
Is it okay?
Yes, sir. It's visible.
Incremental
Yes.
similarity update. So we introduce this. It is not purely branded new, but this one is quite same as the what is called is Jacquard similarity measure. But what essentially we did it, we update this Jacquard similarity. We update this Jacquard similarity incrementally this way. Okay, now we talk about the we are updating the tendency, but how did we make this item tendency personalized? This is also a very simple way. What we did it, instead of taking the all user rating, what we did it only we will take the rating from the neighbors of the users. So that is we have taken instead that formula earlier. This part was not there. We are taking the formula from the all user rating. Means that means user rated a particular item. All ratings we are taking instead of taking from the rating from the all user. We are taking only from the neighbors. Okay, and then personalized item mean also we compute it like that. So another important I will complete within 2-3 minutes. It's session-based recommender system. Why session-based recommender system? That I will do. Long-term user models are often not available for a larger fraction of the user. User could be the first time on the platform. Okay. So therefore, how do you tackle that scenario? So for common e-commerce company, more than half of the all sessions are non-logged user. So earlier, whatever we discussed, even the streaming scenario, we saw one has to log in and then should get the recommendation. But what about the flying users? So we don't have any past information about the user. In that scenario, can the recommender system really help us? So, but because there are not much work on recommender system, only 2.53% of the all session convert to the transaction. Finally, they after doing the what is calling window shopping, people don't purchase it. Okay, so but basically, what if you keep the good recommendation, that can be converted into the transaction. That is the all about the session recommender system. So here is the problem formulation. What do we do? We should give a set of sessions, that is x1, x2, xn. What is those? So which item that user has clicked. So x1, x2, these are the set of item. Can we really predict the what item he or she will predict after xn? That means what item. So a set of item will predict for recommendation. This is all about the session based recommender system. Is quite little different from the earlier. Okay. So here people started using RNN, as you are aware, with a special kind of neural network, which basically very good for the time series data. Okay, I don't want to go in details, so just want to use this algorithm. How session based people use this RNN that I will talk. So this is the basic idea of the GRU. So it will have the what is called is forget get and then update gets, and this is quite formula is quite known. So that is, if we have really want to update it, so then if the JT value is 1, so then we'll update this value, otherwise we will keep the old value. So this basically solve the problem of a vanishing gradient. So in neural network, so they use this one. So here is they use the GRU. Obviously, input will be the session, and then output will be the item to be appeared. So here, what is the contribution for this approach? I must share with you. This is the first algorithm introduced in 2016. As you see, this recommended system, people are quite late of using the what is called is deep learning technique in recommendation, because there was a myth that recommender system is not very good place to use the deep learning technique for any recommendation. So therefore people was delayed, but this guy was the first to tell, okay, we can also use the deep learning technique for session based recommendation. But of late in 2019 on ACM transaction paper also says ki, okay, this algorithm is quite good for a particular data set. So there is a really debate whether the deep learning technique is good in recommender system or not. So this is okay. I have 10 minutes. So RNN is used, and they introduce a different loss function here. So they have the embedding layer, and then a set of GRU layer, and then at the end they have the feed forward layer, and then they have the score on the different item, and the item which has the maximum score will be recommended. So here I need to talk about, see here how this is another problem in case of the RNN, how the information will be fed to the network. So let's say we have the 2, 3, 4, 5 different sessions. What essentially it is that I11 will be the input and I2 will be the output. This is done for the RNN. Similarly, I11 is the input for this session, but at the same time this will be output. Similarly, I2 will be the input here, and then output will be I22. Similarly, I31 will be input and I32 will be output, and so on. And since I4, after I4 we don't know output, so I4 cannot be used for session. Whenever I4 is completed, after I3, output will be I4, and then we can fit the other one in here. So that way they did it, and they got some interesting results. They introduced a different loss function. Here, loss function is, that means the item rank, they use the rank. So rank is lower, means item is more important. So this is all about. So there is another work in 2000 again in CIKM. So they introduced the encoder decoder technique for capturing the. Say, I can explain from this figure. Say, this is the current session. So actually, main objective of this guy to purchase the T-shirt, but sometimes she mistakenly or intentionally click on the trousers also. So then if you take the overall values, then they will recommend this way, first t-shirt and then trouser, and often sometimes also the shoes. But what essentially they did, what is the main intention of the user? Which one they want to purchase, or or he wants to purchase? So that needs to be captured. Apart from the what is the overall idea of what to purchase. Okay, so they use for this one is for the global recommender system, global recommender, and the local recommender. They use the encoder decoder obviously in RNN and technique. So this is all about the technique they use. Okay. Now in next 7 minutes, I'll talk about what we do in our lab, in intelligent data analysis lab. So I have quite a good number of students. They work in different areas. Some of the students they work on e-learning, and some students also work on what is recommender system in the core area of recommender system. Some students work on anomaly detection, and one student is working on trajectory analysis that I will tell with each work in one slide. Yeah, we have a sponsored project from the ACRB. So it's the development of psychocognitive recommender system for the weak learner in flipped learning scenario. Basically, flipped learning means that in traditional learning, student used to come and teacher used to give lesson to the class itself, and therefore there is a lack of proper problem solving session. So in flipped learning, it is in other way around. Students will take the lesson at home, and then in the class they should solve the problem. But with this problem, what happened? Whether student really they were attentive while watching the lecture video at home or not, it is really difficult to identify. So in this work, what we do it, we'll provide the headset to the student. Headset is the EEG headset. Will capture the brainwave while watching the lecture video, and that brainwave we started analyzing, and from there can we identify whether the student was attentive or not. So that is the all about the first work one student is doing along with two MTech student. Another project was by DST, again is for ACRB. So development of a traffic dashboard using social media data and historical GPS trajectory. Basically in this work, what we do it, so we capture the information from the Twitter. So because we have taken the Twitter handle, we use the Twitter handle of the city of Bangalore, because they are quite very frequently they tweet the information about the traffic. So therefore we use that Twitter information along with that some GPS device we fitted with the few device, and then we match these two and then recommend, and then we analyze the data. So this is the entire figure, and we started doing this one. And then of late, we started doing some different work is design and development of e-learning platform for assisting underprivileged school students in Rourkela region. So this is sponsored by MAKAUT that we started just 6 months. Essentially, this is the block diagram or work for this work. What we thought of doing. So for school student, it is like even this region is Rourkela is mostly tribal dominated region. So heavy 51% is population is from the tribal category, and they have their own language. Even they are quite different from the Odia language. So if the student teaches in a class, can those lecture notes can be converted into their own tribal language and so on. This is one thing. Otherwise, other aspect of this work is like we'll send that lecture video will play in the local cable TV, and will inform the parent that there will be schedule. Can your ward can watch the lecture video at this scheduled time, but that should be translated into their own tribal language, because we cannot expect that student parent also should know the English or Hindi, even the some cases Odia. So therefore, we have that challenge to how to convert the even the Odia or English or Hindi should be converted to the local tribal language. So and this is all about our other works here. And these are the few references here. And then I must be thankful to my students for preparing some of the slide here. And my PhD student is Sumanto Datta, and the other students they got the degree, and so on. There are some announcement here. There will be a fellowship-based research internship. We applied for the Vrittika if we got it. So there is a chance that we can take 3 students as fellowship-based internship in the month of May. I don't know how it will be conducted. And then from tomorrow onwards, we have a 3-day webinar on annuity sponsored by MITI. So this is the email, and then you can get the information in the Google site. So I am done.
Okay, thank you, Dr. Patro. I think there are some questions. If you can answer the first questions from supervised versus unsupervised, which is better? Second question, can the association method of multimedia criteria decision making based used for recommendation system?
Okay, what is the first question? I missed that.
Supervised versus unsupervised, which is better?
See, if you have the supervised technique, should have the training data set. So if you have a training data set, obviously you should go for the supervised techniques. That is no doubt. Okay. So, but in some scenario, if you don't have the training data set, then you cannot apply the supervised technique.
Can the association method of multi-criteria decision making be used for recommendation system?
Multi-criteria? What is that?
Can decision making system? Can the association method or multi-criteria decision making be used for a recommendation system?
Obviously, this is really good suggestion, I will tell, because no one explored the association rule for recommendation. Obviously, it must be used, but I didn't see any work over it. This is a really good suggestion. Even I also try. Okay. Hello.
Shantanu sir, please unmute your mic, sir.
Hello.
Yeah, it is okay. I am audible, right?
Yes, sir.
Okay.
Am I audible now?
Yes, sir. Yes, sir.
Yes.
There are another question.
Yeah, I can see also some.
Which model is used today for?
Yes, yes.
Yeah, you can answer.
Which question? One question I can see, sir, how to overcome the biasness of the recommender system in general. I can see one question.
Yes, sir.
Can I read the question and answer?
Yes, sir, sure.
I see one question from Sanjay Kumar Pal. How to overcome the biasness of recommender system in general? Okay. So actually, what I said, of late people started working over it.
Yes, you can answer.
Yeah. Of
Yes.
late,
You can answer.
yes, I am answering. Okay. So of late, people started working on how to overcome the biasness of recommender system. Okay. So we have a work published in expert system and application. We use complex techniques, like we use the Siamese network, and then Siamese network. That is, we use the Siamese network in an unsupervised fashion and so on. But one simplest way in general answer is like, see the item which has very less rating, we can inject the rating, false rating we can inject, and we can see the effect. So that is another work we submitted the work. So we injected the false rating to the item which has less rating. Okay. Say so next question is from Sayantani Saha. How the strict user recommendation is used in the system, how it is affecting the overall rating. Okay, so strict user rating, as I said, that adjusted cosine similarity, basically they take care of the strict user in case of the user based, and for in the what is called is in model based approach, basically there is something called item biasness and user biasness, so they take care of that. And one question I see from Vidyut Das from HIT, which model is used today for the recommendation system? This is very difficult to answer. I asked the same question to Amazon guy in 2015 one conference. They said we cannot disclose. But I said 2003 one paper talk about they use the neighborhood based approach for recommendation. That's all. I think these are the questions.
Sir, I have one question. Is it possible to apply these recommended systems in the field of security also? So we actually try to go to different sites. So which site is secure? Which of whether a particular tool, software tool that is malicious or not? Can we apply this kind of system in the field of security also?
There is something called trust, right? Trust in security. I think you people also work, but there are some work where people use the trust information for recommendation. I think one can explore that, but I am not in much with trust and others in recommendation. Okay, but obviously I think there are work on which people use the trust for recommendation. I'm not audible. Kosik Babu, Kosik Mojum, sir. Kosik sir, I could not hear you. Yeah, now it is fine. Yeah.
Yes, sir.
Yeah.
Thank you, sir.
Yeah.
So I think we have no more questions. Shantanu.
Okay, fine.
Okay. So thank you, Dr. Patro, for the illuminating and informative lectures. I think participant has gained a lot of knowledge from the today's discussion. On behalf of the committee and the department, I thank Dr. Patro for his enlightening and encouraging lectures. Thank you. And for the participants, I'm saying that you direct link with this end with this year and already shared, and I will also request you to join tomorrow from 10 Dr. Tito Sane the lecture from tomorrow 10.
Okay, thank you.
Thank you, Dr. Patro.
Thank you, sir. Thank you.
Yeah.
Thank you so much for taking time out and coming here. Thank you, sir.
Okay, thank you.
Okay, Prem. So we can end the session now.